Hello.
Hey.
By the way, I would like to understand, let's see what page is the best one for this. But I mean, sorry, back to this question of what it means that all these formal systems are being Rosetta Stoned by our efforts. I mean, you know, okay, where has one seen this before? Well, clearly one place one's seen it before is universal computation. Another place one's seen it before, I mean, you argue that one's seen it before in foundations of math kinds of things.
Right.
But I mean, I don't know that history. Well, I do know that history. And I think, so the question is, what does it mean if everybody invented the same thing, basically? I mean, the most common case of that is universal computation. You know, people invented lambda calculus, they invented Turing machines, they invented whatever else, and they all turn out to be the same, right? But those turn out to be the same in, you know, they turn out to be the same in terms of compilation. The question is, when all these things are turning out to be the same, there is a weaker form of compilation, presumably, between them. It's not full universal computation. It's something much weaker. It's a much more direct.
What makes you say that?
What's that?
What makes you say that?
Well, I mean, look, it's a trivial statement.
Universal computation.
What's that?
Graph rewriting systems are capable of universal.
Oh, of course they are, right? But I mean, it's a trivial statement that all these things are equivalent if, you know, if they're just equivalent to Turing machines and therefore they're all equivalent, right?
Right, but the interesting case is, can you define a compilation language which makes the encoding straightforward?
Exactly.
But so, and that's what our project has done. In the same way as set theory made the encoding straightforward between different.
Okay, but I'm gonna argue it more precisely.
Structures.
Okay? So another case of this was polynomial time computation, right? That was a case of an encoding that was a rather straightforward encode. Well, not necessarily straightforward, but it was a bounded encoding.
Okay.
Right. So the question here is, when we see all these things being equivalent, right? It isn't a full compiler for an arbitrary Turing machine. It's a much more bounded thing. And the question is, what is our way of characterizing that boundedness? Right? So in other words, these different systems, I mean, is it like computational complexity theory, or is it some other form of bounding of the translation machine?
I don't understand in what sense it's bounded. We have two universal models of computation, and we can prove that one can simulate the other with an encoding language that is itself trivial. Are you talking about the boundedness of the complexity of the encoding language?
Yes, I am, because that's what.
Right, fine. Yes, then that's interesting.
Yeah, right. So the interesting question is, just like people found that it was a useful bucket to say all polynomial time computations, the question here is, when we look at all these different systems, whatever they are, interaction nets and versus, you know, some category theory thing versus this versus that versus the other, you know, POW cow sets and so on, POS cow sets, whatever. You know, what does it mean that they all seem to be swirling around the same ideas? And what is the translation? What is the character of the translation between them?
Right.
I mean, to me, right, it feels like the translation is very linear. I mean, it's very straightforward between most of these things. It doesn't require a big, you know, it doesn't even require, if you were doing it in terms of computational complexity theory, it would be pretty direct, I think.
Yeah.
But instead, you know, what this is.
Again, so yeah. How is this any different to the foundations of math situation?
Well, I don't know what that was unifying particularly. I mean, in modern times, that's a thing where given set theory, you can build a bunch of things on set theory. But it's not like when set theory came in, people didn't say particularly, oh yes, that unifies this and that. I mean, it's a slightly different situation.
Didn't they?
Don't think so. I think it was an extremely obscure thing that, I mean, well, okay,
maybe, okay.
I'm not sure.
Maybe I misunderstood the Begriffsschrift.
That was a previous effort. That was the Frege effort.
Yeah.
which was eventually.
But was the first text that I was able to find historically that postulated that things that were sufficiently different as functions, groups, natural numbers, etc., might all just be instances of the same object.
Fair enough. Fair enough. I mean, that was a. Okay. Okay, but let's understand then what. Okay, so there are two questions here. One is, I mean, there's also the question of, Turing machines, lambda calculus, things like this. They have their domains of utility, even though they're ultimately equivalent, right? But they're things better thought about. I mean, like combinators are the all-time loser, in the sense that people have not been able to reason in terms of them in the last 100 years for the most part. So the question is, what?
Right. Isn't it just a minimization problem? I mean, you have, as you say, combinators, you have lambda calculus, recursively enumerable functions, post machines, whatever. But it just so happens that in the ordinary language of human expression, Turing machines are one of the easiest ways to express that abstract concept of universal computation. And so the kind of base language that gets used is Turing machines in that description framework.
Well, I mean, I think, look,
and the same thing is happening here, right? That we have what is either minimal or close to being the minimal representation of this fundamental concept, whatever it is. Right. And so we have produced the analog of the Turing machine, but for whatever it is that we've discovered.
Yeah, right. Well, fair enough. That's a way to think about it. I mean, I think that I mean, so then the question would be, okay, so then, that suggests that in terms of a mode of operation, right, that writing the compilers. So for example, I mean, it is sort of bizarre that I was considering yesterday, I was trying to avoid writing a Turing machine causal graph generator, which I eventually wrote because I got too frustrated and just decided to write it, which took all of about 10 minutes or something. But what is sort of interesting there is that I seriously considered simply using whatever it is, one of these ones here, that is, just using the translation, just using thing that translates into our models, and then use that as my way of computing the causal graph for a Turing machine, if that makes sense.
Yeah.
So what that suggests is that the dictionary we should create is literally a translator into our models from each of these things. I mean, because that would be, but I mean, the question is, okay, I mean, so to operationalize that, I mean, I don't know how implementable these models are and whether they have reasonable notation and things like this. Do they?
Which models?
I don't know, any of these things. I mean, the pos cows, I mean, each one of these things has, or interaction nets for that matter. I mean, looking at these pictures, okay.
Yeah, so we can implement, we have ways of implementing multi-way systems and graph rewrites, if that's what you're asking.
Of course we have.
Yeah, so I don't understand the question.
The question is, okay.
A POSCAL is a multi-way system. An interaction net is a graph rewriting system.
I'm well aware.
We can write a translator between lambda terms and interaction net terms. That's a trivial piece of code.
Okay, but the question is this, I guess.
I could write a function repository entry if you want me to.
Yes, I think that would be, but I mean, I'm trying to organize the meta level version of this, right? That is, we're discovering that all these different things are equivalent, right?
Yeah.
And
can I point out an aspect of this that I actually find quite interesting?
Yes, please.
So in exactly the same way as the multi-way interpretation of quantum mechanics implies that there's a generalization of quantum information theory which also considers the complexity of the measurement operation.
Mm-hmm.
I think this general framework implies there's a generalization of both computability and computational complexity theory, in which one considers not just the intrinsic complexity of the computation, but the complexity of the encoding or the translation operation.
Yes, wouldn't that be lovely?
right? So when you say Turing machines are equivalent to lambda calculus, I guess this comes back to the boundedness thing you were saying, right? There's potentially a way that you can give a quantitative description of how equivalent they are in terms of some computational complexity of the encoding transformation.
I agree. That would be quite wonderful, right?
And I mean, that's probably just the Rulial space measurement. I mean, okay, my conjecture is the same thing that gives you measurement in the pure multi-way case is if you then apply that same operation to a Rulial multi-way system, will give you effectively the same thing.
Well, isn't that a nice topic? Because that was actually what I wanted to talk to you about.
Okay.
Because I have data, right?
Okay.
Of course, I've been doing zoology. Okay, so you've seen some of these creatures.
Yep.
There are more creatures now. Except this is so unbelievably slow for some reason. So that thing in the middle of the screen there is the Rulial multi-way system for 2-2 Turing machines. Okay.
Yep.
Okay, so these are slightly more trivial ones. I don't know if you've seen these. These are basically no tape data Turing machines. Okay, so there's some kind of marker. They probably have a name. I think it might be called marker automata or something. But anyway, they just have all they do is they
move around and they change state.
That is correct.
Right.
And this is okay. So that's their multi-way graph.
Okay.
Not too surprisingly.
Right.
Okay. Okay. So first statement is, what is the limit of the Rulial multi-way graph? Okay. And the answer is, whatever it is, it's an exponentially, it's an exponential dimensional space where, not too surprisingly, it's completely dominated by tape states.
Yep.
Okay. And it isn't, these things aren't precisely to the end, but they're close. Mm-hmm. Okay. So consider finite tapes. All right, this is going to be relevant, and it has a math problem that I haven't been able to do yet. So there are a couple of different ways to make finite tapes, but anyway, you can make these. This is a cyclic tape. Okay. Okay, so here's what comes out. You've seen some of these pieces of mail, I think. Lovely. All these things are. Oh gosh, why is it so slow to scroll? I don't know. Yeah, these are ones where it's a different way of bounding the thing to be finite. Oh, this scrolling behavior is just infuriating. I don't even know why it's so slow. Oh, and it freezes my whole computer. Did it freeze the Zoom session as well?
No, I don't think so.
Okay, good for Zoom. It managed to. Gosh. Anyway, so the question here, we have a concrete example. Now, come on, why is this so slow? You know what, I need to. Sorry, I guess this computer is slower than my usual computer. Hold on, I just want to send mail for. Yeah. Just a second, just a second. Something is. Just reporting this slow scrolling behavior. Okay. All right. Oh, that's, by the way, something yeah. Okay, so first question, I mean, this is just a math homework question, but this, so these graphs, okay, are Cayley graphs of groups, I think. And I think that the group relations you can write down. But I can't figure out which group this is. And this is, you know, the friendly geometric group theory stuff will tell one, once we have this limit, is going to tell one the space of non-deterministic, you know, the space of non-deterministic Turing machines. And that I think is relevant for what you are talking about, which is this translation stuff, because this is the space in which translations operate, so to speak. This makes sense?
Yeah.
So I don't know if you have a brilliant idea how to do this. I mean, I believe these are the relations. I believe you can represent it two ways. You can either represent it with 4 generators or 3 generators. And, you know, the achievement as of a couple of days ago is to show that for the case of size 3, this is the group, A4 cross Z2.
Mm-hmm.
But the question is what the limit is. Well, anyway, okay, that's one. Do you have any bright ideas about how to think about doing that?
No, I'm not aware of a general procedure for identifying the name of a group from its collection of generators.
Yes, indeed.
For its relations.
I know that. I'm asking the, I mean, I don't even know if we can guess what the form of the, right. I mean, it might also be obvious what this group is, because it involves, you know, a very limited set of operations. Anyway, okay.
I mean, there are certainly classification theorems for things like finitely presented groups that we might be able to use. Like, I mean, at the very least, this will tell us. Well, this will tell us something.
Well, the classification theorems just say there is a classification. But one thing that's interesting here is there's a family of these groups, right? As you change the n, as you change the length of the tape, you will get a different group. So this is an infinite family, right, of groups. And the question is, I'm trying to understand what's the limit.
No, I understand. We're asking for some infinite parametric family of groups that all satisfy this presentation. And then what happens is that, you know, what happens is the parameter in that family goes to infinity.
Right, and actually, I think that, right, and it's a limiting group that probably is actually the infinite group. I don't know how to think about the fact that L to the n equals 1, which is the cyclicity condition. I guess that condition, L to the infinity equals 1, probably just that condition just goes away. And there's then an infinite group that has only the other conditions. I bet that's right, actually. Relation probably goes away. Well, it'll be shocking if I actually have to find an actual group theorist to help me with this. I was trying to, yeah.
Well, I mean, if you want to send me the list of relations, I can try and I can at least come up with what the constraints are.
Here are the list of relations. Right, I sent them out multiple times, but here I'll send you the I'll send you this lovely. I mean, this is all in Dropbox, but nobody seems to be able to find anything in Dropbox these days. Okay, so I think the first one is easier to understand. The second one, I believe, is still correct. And the second one is a direct generalization of what we actually know from that A4 cross Z2 thing. All right. So what you're, I mean, just for what it's worth, by the way, this case horribly fails. This is the causal graph structure instances.
Yeah, of course, as we discussed.
Why does it fail?
Because I haven't incorporated step number or state ID structure yet, which I will do in the finalized function repository entry, but I haven't heard back from Jan.
Oh, for goodness sake.
But yeah, so all of the instances stuff requires, it internally uses step numbers, which I didn't include in the multi-way Turing machine.
Let's see.
Let
me just send out mail about that question.
And by the way, I mean, hopefully Sushma already did this, but make it clear to Jan that he only needs to send, like, he doesn't need to integrate anything. He just needs to send me the rendering functions.
Okay. Okay, what do you think in these things, what is it going to look like? What, you know, these, is it obvious what? I mean, I think see, the deterministic Turing machine causal graphs can have different forms. But I don't think I don't quite understand how it will slice apart from the multi-way causal graph. In other words, these are very bizarre slicings of whatever is happening in the multi-way causal graph. Does that make sense? I mean, because in fact, what you find is that and this is relevant to what we're talking about here, the deterministic Turing machine path in this overall space is something quite weird.
Yeah, it's not a geodesic, as we mentioned.
It's not a geodesic.
Right, obviously, because, well, P and NP are not obviously the same.
Right, but so in a sense, the ball in this picture, the ball is all configurations that can be reached by a non-deterministic Turing machine.
Yeah.
Whereas those other pictures I was drawing, showing everything that can be reached by a deterministic Turing machine, those represent the sort of, I don't know whether it's polynomial, at least the linear ball for all those Turing machines, if you see what I'm saying.
Yeah.
So in a sense, the question of, you know, what can, okay, so here's a question. So if we think about essentially light cones, translation cones, whatever we're thinking about, in this graph, right? So we're starting from different, so for instance, that's the deterministic Turing machine light cone, so to speak, within this graph. I'm trying to understand. I mean, so let's say we have two different starting points, two different configurations. We start them off, they have two light cones in this space. What is the significance? So in other words, see what I'm asking? The thing I'm trying to understand is, this is an example of where, okay, so the translation from one deterministic Turing machine to another, for instance. So first point is, there is presumably a deterministic Turing machine that translates from one deterministic Turing machine to another.
Yeah.
And so what that means is, in this graph, but there's also a non-deterministic Turing machine that does that translation, which is basically, I think, geodesics in this graph from one, right, so there's one squiggly line here from one deterministic Turing machine, there's another squiggly line for another deterministic Turing machine. There exists geodesics that connect those two in this graph.
Yes, translation is the analog of a P form.
I have to unpack that statement. So, I mean, So where
So,
P is
so
2 in this case, where if they're two Turing machines, if we're translating one Turing machine to another.
yeah, then it's a bilinear differential form.
Okay.
Because
Right.
all you're doing is you're doing the same string diagram construction that you would do in the hypergraph or the causal graph.
No, I know. But so
yeah.
what's the significance of that? So we're taking this and...
Well, that was the point I was making about measurement.
Well, that's why I was bringing up these pictures.
Right.
Right. So let's just try to understand that. So we've got these two different paths, and we've got this kind of surface that joins this membrane that joins these paths.
Right.
And that surface has a certain area, among other things.
Mm-hmm.
Should we wish to discuss that? Or it has, I mean, the endpoints of those paths have a certain geodesic distance between them. And the whole path has a certain area that is spanned by those two paths.
Right.
Okay. And
which means, amongst other things, that there should be a nice complexity theoretic interpretation of the Grassmannian, and vice versa.
Okay. You are so fast. I mean, yes, I know that there's obviously okay, hold on. Let's just...
Which is cool, because I'd never thought of that before, that the Grassmannian is somehow, in Rullial space, the Grassmannian is some complexity theory measure.
I know.
As you say, it's kind of obvious.
Right.
Ooh.
What?
But that leads to questions about spin groups in Rullial space.
All right, listen, this is our very first example of an actual Rullial space, right? Always good to look at. It would be nice if we knew what the actual underlying space is. And it's going to, I mean, we do know it's vertex transitive. That's pretty obvious, right? The thing that you get is vertex transitive. I think it's pretty obvious it's a Cayley graph.
Sure.
I think that's sort of useful. I mean, the fact that there's translation invariance in this, that means that, first thing it means is that every initial condition is kind of, it's a uniform space. Every initial condition is equivalent, so to speak. Right? So given two initial conditions, go ahead.
I actually wonder, just hearing you say that, whether universality necessarily implies a certain homogeneity condition.
Well, I bet it does.
I bet it does too, because basically, if you could get to if you had some initial condition where sort of going out some finite distance wouldn't give you something that looked globally like the rest of the space.
Exactly.
I don't think it can be universal. Yeah.
Right. So, okay, first comment, at least, okay, so let's think about this. For TMs, the underlying Rullial space, well, the underlying Rullial multi-way graph is, okay, so there's a different question, which is the actual Rullial slices of this thing is translation invariant. Okay, so that, and some form of, I suspect, some form of quasi-invariance is necessary for universality.
Mm-hmm.
Probably doesn't have to be, in other words, what it means is there has to be a finite translation for any different position in this graph that you're starting from. It has to be, for any different machine that you're using, it has to be, there's a boundedness.
You can't have a trapped surface.
Let me understand that statement. So, I mean, okay, so in other words, i.e., there is a boundedness to the deformation of the geometry. What is your statement about trapped surfaces? So you're saying,
if you have a trapped surface, that's a collection of initial conditions from which you can't reach the rest of the universe.
Is that really? Well, what if it terminates? What if there are a bunch of initial conditions for which I guess it can't terminate? I mean, I guess in this non-deterministic thing, it can't terminate. There is no notion of termination.
Right.
I think. So well, in the multi-way graph. So the first statement is the multi-way graph is infinite, right? So that's the first thing you need for computational universality. Implies ... So first, the multi-way graph is infinite. Rullial multi-way graph better be infinite. Okay, the second claim would be that you can't get stuck. Now, I think that's probably true. Okay, no trapped surfaces, i.e. you can't get stuck. No termination. That means no space like a time like singularities, i.e. you can't get stuck. Yes, okay. So hold on a second. So you can't get stuck is the statement that there always exists this transformation between paths here.
Right.
I.e.
Yeah, I mean, that's just the statement that the universe is causally connected.
Right. Between deterministic computation paths. Okay, so the next point claim is, okay, what is a deterministic computation path? Deterministic computation path, and what is the analog of a deterministic computation path and anything else we've studied? Because most other things we've studied, most of what matters is GD6. These are not GD6.
No. These are generational multi-way paths, I think. Something like them.
Yes, there's something like that.
Because I think the analogy between non-deterministic and deterministic paths is the analogy between multi-way paths and classical paths.
Yeah, I agree. So somewhat like generational multi-way paths, but no, we should understand that analogy. So let's also understand super quantum mechanics, okay? The quantum mechanics of Rullial space.
Yes. So this is the thing that I'm now quite excited about, which is this notion of that measurement and encoding are the same thing.
Right. Okay.
Which probably people who work on foundations of quantum mechanics, maybe some of them already knew that. But
in what sense of no? I mean, the no that has to do with, can you translate this path into one over here? Right. That's the
right.
Okay, so let's come back to, all right, so we've got a deterministic computation path.
I think that's a nice way of thinking about computational encoding. It's like, so you have your ray in this Rullial Hilbert space, and then you have another ray in the Rullial Hilbert space, and you're asking what's the projection of one onto the other.
Yes, I agree.
And that's basically, I think that's a nice
the non-deterministic encoding.
Yeah, right.
Right. So okay. So encoding is the string figure slash projection slash whatever slash p form that leads from one let's say deterministic path to another. Now notice that here's an important point. Okay, so for deterministic paths, okay, so there's translation invariance, translation transformations, translation of deterministic paths, right? So they do not.
By the way, if we start saying translation invariance, that's going to get super confusing.
Oh, it is, yes. Oh, shoot. What are we going to call that? Position. Yes. Okay. So what are we going to call this? Ba, 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 ba.
Mappings. Yeah, I don't know. Sorry, go on.
Well, configuration motion. That's a bad idea as well, because Turing machines have heads moving back and forth. Resetting the initial conditions. That's not going to work either. Let's think. Well, rule motion.
Okay, yeah.
That's okay. I.e. changing the initial conditions, right? So it is not the case that it's invariant under rule motion. A deterministic path is not invariant under rule motion.
Mm-hmm.
But what is it? Under rule motion, that represents what the Turing machine does, basically.
Right.
There is no invariance. Instead, the thing will flap around all over the place. Okay, but if our translator is non-deterministic, what is the interpretation between two generational paths, generational state paths in the ordinary multi-way system? What's the interpretation of this string figure thing?
Interesting. Yeah, so it's like you have some. It's probably I don't know. Maybe it's just reflecting what I was reading about earlier, but it's probably related to these Frobenius algebra things. But it's like it's the case where you have a purely classical system, but you're performing a quantum measurement with respect to a different purely classical system.
Yes.
And I'm not immediately
aware. Is it a
aware
change of basis story? I mean, go ahead.
I guess you could think of it that way. I don't know. I don't. The answer is I don't have a good way of thinking.
Well, okay. So I'm gonna make a claim. Okay? It is a rotation in multi-way space. I mean, that we already know. It's because that's our interpret. So what does it mean?
But this is the point that all such things are interpretations in multi-way space, irrespective of whether they're classical trajectories or not.
Well, I understand that, right?
So the question is, what marks out the case where you're just dealing with the generational states?
Yes.
And
okay, can we go back to rule space and talk about the analog of generational states in rule space?
It's probably. By the way, this may be. This is probably also related to this issue of interference, of just purely destructive interference. Because if you're projecting two pure multi-way, generational multi-way paths onto each other, then they can only be because all the space-like separations have been eaten up by the two paths, so to speak. All you're going to get between them are branch-like separations.
Yes.
So if you then attempt to perform a completion procedure, that's going to be a purely destructive completion procedure.
I don't understand that. What do you mean by a destructive completion procedure?
Because the only places where you get, so when you have something like a 1 0 and a -1 0,
yep.
And we say that they destructively interfere. The reason they destructively interfere is because there's no space-like distance between the places where they differ, in the first position.
Right.
So it's a pure branch-like separation story. And so when we attempt to perform a completion procedure, we get destructive interference. Whereas if we had 1 0 and 0 1, then there is a space-like separation, and so then you don't get destructive interference. You get a 1 1 when you do the completion.
Well, let's just understand that. So you're saying when they are on top of each other. So in terms of multi-space, right? Once we have our concept of multi-space.
Yeah. Okay.
What?
I don't yet have a good intuition for multi-space. Because I'm not.
No, nor do I.
I'm not yet sure I understand what it is.
Well, okay, let me explain what I think it is, okay?
Okay.
I think it's this thing where, sort of looked at from a great distance, it looks like ordinary space. But more locally, it's bubbling out all over the place to show the variations, to show the branch-like direction variations.
No, I understand. I understand that bit. I mean, am I right in saying it's like a branchial graph, except where the space-like separations are treated as the sort of network, and the
Yes.
branch-like separations are kind of fuzzed out somehow.
Well, the branch-like separations, look, I think it's two kinds of networks. It's the branch-like separations. It's like as if you lay it out on the plane, the space-like separations out on the plane, and the branch-like separations are coming out of the plane.
Okay, so it's an annotated branchial graph.
I think so.
Okay.
Yeah, that's a way to think about it. Yeah, that may be a good way to think about it. I mean, it's an annotated branchial graph whose layout, for our purposes of understanding, is what I'm saying roughly.
Yeah. No, actually, I like the idea of having the two things in different dimensions, so to speak.
Yeah, right. I mean, it's like our picture of the space, time, and branchial space. Yeah. Which I think is a good picture. And I think this is, branchial space, we're just orthogonal, making it orthogonal to ordinary space. Now, it's going to be much messier than that because, in simple cases, I think we'll be able to draw pictures of multi-space that aren't completely crazy.
Yeah.
And you can also think of it as a nice simplification of a multi-way causal graph, because we can do the multi-space analog of the space-time causal graph.
Yeah.
Right? So, which is essentially a multi-way causal graph that has its space-like edges in some sense. Well, it doesn't have it has its.
A space-time causal graph would be something like a horizontal slice through multi-space.
Space-time.
No, vertical.
Well,
a vertical.
Well, a slice, like a slice in the plane of space-like separations.
Yeah. Right.
Yeah, except I'm sorry, no, but going down because we're not talking about time in that case. So it's a cross.
One causal network slice would be a horizontal slice through multi-way
something
space.
like that. Whichever way is up. But anyway, okay. So
right.
Okay. So then So where do we get back to the multi-space thing? So the claim would be that destructive interference is the statement that in multi-space, there's just at a given space-time point, there is simply a stack of branchial things that all do something different.
Yeah, right. Yes, it's a vertical tower in multi-space. Right.
And so that tower is, so then the question is, when we measure that tower then, in other words, to say something definite happened at the space-time point, we are using, for example, your completion idea to make that measurement.
Right.
And just to understand what that means, so what that will correspond to is, in that vertical tower in multi-space, the statement would be that the space-time configurations in that vertical tower are different. Right. That is, the context of it is the same, as in, around that vertical tower, the, space is knitted around that vertical tower so that we know where it is. But once we look at where it is, there's ambiguity in the vertical tower about what's actually in space at that point.
Right.
Okay, so now let's imagine the completion procedure. So let's imagine we try to measure that, which means, boy, how do we think about this? So let's see. I mean, it is, I'm now getting a pretty good picture of what the pictures of multi-space should look like. Okay, so in this case, right, what we'll see is, okay, what does it mean to do a completion here? So this multi-space is a projection, is a transversal of the multi-way causal graph. And well, a completion is a projection, is a squashing of multispace is a compression of the branch field direction of multispace.
Right.
Right? Now, what kind of a compression is it? Can it be thought of as an averaging, as in branch field space, when you make a completion, when you say this is equal to that, are you effectively averaging those two things? You're ignoring, you're just removing degrees of freedom. You're coarse graining those degrees of freedom.
Exactly.
Okay.
So when there's space-like separation, and in addition to vertical elevation, it doesn't matter. You do the averaging, and nothing gets deleted.
Exactly.
But when there's pure branch-like separation,
this is a good picture.
Space-like separation,
this is a good picture.
Yeah, right. There isn't.
This is a very nice picture. Right. So basically, what this is saying is that in multispace, measurement consists of trying to make the branchial layers agree to the point where you say something definite happened.
Right.
Right? And how do you make them agree? Well, you coarse grain. And when you coarse grain, the that's nice. That's nice. When you coarse grain the thing, I mean, and we have to think about why there needs to be coarse graining and how the coarse graining observer fits into the whole thing. But basically, the picture is when you coarse grain, you get, if there was just complete inconsistency in the spatial structure, that all gets zeroed out, so to speak. Very nice. Very nice.
Anyway, so as I was saying, so then the generational multi-way case where you're projecting one classical system onto another is just an extreme version of that destructive interference situation.
Okay, so let me just make a note of this multi-space interpretation. Okay, in multi-space, there is the horizontal plane. God, we got to get pictures of this. The horizontal plane is ordinary space, bubbling out in the vertical direction as branchial space. Measurement consists in coarse graining in the branchial direction. By the way, there's probably also coarse graining in the spatial direction. And that's probably corresponds to something different, right? So it's the coarse graining in the branchial direction to get a consensus. Why am I reminded of blockchains?
Right.
Why am I reminded of blockchains? Because this is in fact the same problem as in those distributed things like that IOTA blockchain thing.
Of course, yeah.
To get a consensus, okay, to get a consensus result, quotes classical result.
Right.
And the whole point is that the question is, do you get a consistent classical result? Let's see, if you do the same coarse graining everywhere, you are sort of guaranteed to get a consistent classical result, I would claim.
Right.
In other words, if you do a uniform completion everywhere, you'll get a consistent classical result.
Right.
Okay, so the claim is,
and this is a nice pedagogical way of explaining the fundamental difference between quantum mechanics and statistical mechanics.
let me understand that in a second.
Quantum mechanics is coarse graining in the branchial direction. Statistical mechanics is coarse graining in the spatial direction.
Yeah, that I get that. Okay, so you have to, same coarse graining is applied everywhere. You will have consistent classical, well, if you, consistent classical behavior, but you might have to do a lot of coarse graining to make everything classical.
Right.
It might even be to the point where you can say nothing. Okay, but so then let me understand what it looks like. Okay, what does it look like if you do statistical mechanics coarse graining in the spatial direction, but you don't do coarse graining in the branchial direction? What is that? I bet that that's, okay, coarse grain in space, but not branchial space.
It's probably a mixed state. Right? Because it's still a quantum mechanical thing, but you've now by doing the coarse graining in space, you've introduced classical probability.
I agree. So, as opposed to a pure state, so in practice, making a quantum computer, you don't want a coarse grain in space.
Ideally not, because then mixed states are hard to work with.
Right, but so by preventing coarse graining in space, you're preserving the purity of your quantum state.
Right.
Which is to say, don't let any heat get in.
Yes. And by the way, I mean, so this comes back, I mean, the thing you were saying before, that, you might have to apply a lot of coarse graining in order to make something classical.
Yeah.
So in the case where you have a maximally entangled state, I think that, that's an example of a case where you'd have to do effectively infinite coarse graining to get something classical.
Right. What is the significance of a maximally entangled state?
Well, so this is what I'm trying to think about. So I obviously, if you take a maximally entangled state and then you trace out some subsystem, you get a mixed state.
Yes.
And so I'm wondering if that's corresponding to the statement that you can't coarse grain in the branchial direction if it's maximally entangled. You have to coarse grain in the spatial direction.
Well, if it's maximally entangled, no amount of coarse graining is going to resolve the entanglements.
Right. So if you still want to preserve the state, you can't just coarse grain in the branchial direction, because that's going to destroy everything.
Yes, that's true.
So you have to coarse grain in space.
So what?
So you have to get a mixed state. I know this is not. I don't think this is a deep point. I mean, it's finally just clarifying my own understanding of why, if you trace out a subsystem from an entangled system, you have to get a mixed state.
Right. We trace out, right. Well, it's not quite explaining that, right? Because if you have a maximally entangled state, I didn't quite understand that full logic.
So you take some maximally entangled state.
Yep.
It's got lots of vertical elevation,
mm-hmm.
But it also has some degree of horizontal expanse. So now what you want to do is, so one way we could represent tracing out a subsystem is we want to take, we want to apply a coarse graining, but we're only coarse graining with respect to one multi-way geodesic, for instance. We're only projecting things onto that one geodesic.
Mm-hmm.
If you did that coarse graining just in the branchial direction, then you would get perfect destructive interference.
Yes.
So, which you don't want. If you're tracing out a subsystem, you want to have a system. At the end, you can't just destroy all the information. Right. So you have to. So in addition to doing branchial, or possibly instead of doing branchial coarse graining, you also have to do at least some degree of spatial coarse graining in order to ensure that you're preserving the information.
Something. Right. So in other words, in the case of maximum entanglement, you have built a tower in one place.
Right.
And so unless you take essentially skew slicings through that tower, as soon as you're just trying to sort of squash the tower, the only way to squash the tower, or the only way to get something that looks classical or something is to squash the whole tower, in which case you have nothing.
Right.
But you can imagine some skew projection where you've managed to preserve some piece of the towerness, by spreading it in the spatial direction.
Yes, right. Yeah, actually, that's a good way of thinking about it. You can't just project directly downwards. You have to project in some skew direction. I like that.
Right. If you want to preserve the structure of the tower.
Right.
We need pictures of multispace.
Uh-huh.
Is that possible to do from our current branchial graphs?
Yes. But it will require some work.
Right. So, I mean, what we need to do is to make a picture of multispace. But the branchial connections in a branchial graph aren't the same as the connections in multispace.
Yeah, because it's the branchial graph, not for the evolution graph, but for the causal graph.
Is it only that? I don't think it's quite the branchial graph. It's some kind of foliation of the causal graph. It's some kind of representation of individual slices in the foliation, which is roughly a branchial graph, but may not be exactly.
Well, yeah, but if it's not ancestry distance, then what is the connectivity?
Well, okay, but I mean, okay, one-step branchial graph. Okay, so basically, it is a causal branchial graph, a branchial graph for the multi-way causal graph.
Right. That part's easy to do. The difficult part is in tagging the space-like and branch-like separations.
Okay, let's think about what the procedure for that actually is. Okay, how do you tell what's a space-like piece?
Well, I mean, I have a procedure for doing it, but it's not super efficient.
What is the procedure?
You look at the event specifications, and then you use them from the event specifications. Of course, you can reconstruct the input and output states, and obviously where the event got applied, and then you just look for the string overlaps between the places where the event got applied.
Right.
In those
so you're
strings.
making snakes basically of some kind.
Exactly. It's the super inefficient generational multi-way system algorithm.
Okay, hold on a second. So basically, to find which are the spatial edges.
The reason I've been resistant to do this is because it is a very inefficient procedure, but I haven't come up with a better one.
Why don't you write it? Why don't you write this procedure and we can just run it in small cases, because that will give us some intuition about what's going on.
Okay, sure. I mean, but it will be slow on the same order as generational multi-way system, because it will be using basically the same algorithm. Okay. So how do we want to represent this? Should it return an association of edges which are space-like and edges which are branch-like? Or
thinking. I think that's a good start.
Okay. Yeah, and then at the very least, we can construct a branchial graph which is colored by separation.
Indeed.
And I'm also wondering.
But previously, these graphs that we had from event branchial graphs were complete graphs mostly. But maybe that was just.
But that was that's only a function of the evolution history. For the causal case, it'll be different.
I see. Okay, so I think by the time we are considering a branchial causal rulal graph.
Yep.
Actually, a rulal branchial causal graph. The yeah, complicated. Okay, but that's. I'm sorry. Let's come back for a second. By the way, as I say, my embarrassment about people asking about the Born rule and me not even knowing what the heck they're talking about. I am now happy to have learnt why I don't know what they're talking about. I need to find out how it came to be called the Born rule, because it just didn't have that name when I used to be in the business.
Okay.
Or at least it was never referred to in that form. But so for us, just to review.
I'm sure von Neumann definitely calls it the Born rule in his Grundlagen der Quantenmechanik. But okay. it may not have been widely used outside of that until quite recently.
I suspect, you know what I bet it is? I bet it is that yes. You know what I bet it is? I bet it's because of quantum information stuff. That people have looked back at von Neumann's stuff, and that's why it's being referred to that way.
That's quite plausible. Yeah.
Yeah.
After our conversation the other day, I did go back and look through some things, and I noticed I think Dirac doesn't use the term, but von Neumann does. I wondered if there was some change in fashion.
That's what's happening.
Yeah, you're right. It's probably QIT.
Mm-hmm. Okay, so what is the crispest version of how we get it? So I think the answer is that because we're just looking at path counting, because it's a story of magnitudes, what we're saying is the value of a transition function is equal to the path counting of what arrives there, but the question is what arrives, so to speak. Because the paths could just go into la-la land and never arrive at the correct position in branchial space to correspond to your final measurement.
Yes.
So in a sense,
I mean, my crisp version of the Born rule is stating that if you project in the multi-way system between two vectors and you construct this string diagram, then you're necessarily squaring the path weights, right?
Why?
Because for each vertex on one geodesic, you're computing path weights. You're computing shortest path distance to all vertices on the other geodesic in order to construct the string diagram.
I don't understand that. So wait a minute. We're talking about, okay, walk me through this again because I didn't understand that at all.
Okay,
so you're saying
we have two geodesics in the multi-way system.
Yep.
And we want to project one onto the other.
So why are we projecting one onto the other?
Because that's what a measurement is. That's our bra psi ket phi operation.
Well, yes, but it isn't the S matrix. The S matrix is going down the geodesic.
Why are we talking about S matrices?
I'm not sure, but okay. You're just talking about a static in time measurement.
Right.
Okay.
I mean, my understanding of the Born rule is just that it's, the probability is the square of the magnitude of the wave function, right?
Yes.
Right. So all we want to show is that if you take that when we do that projection of bra psi ket psi or whatever, that we end up with a probability which is equal to the square of is equal to the norms of the two amplitudes multiplied together.
You're saying to make a specific measurement, projecting onto some basis state, your claim is that projection, if we looked at the magnitudes of those two, I'm now even more confused. Okay, so you're looking at the magnitudes of those two objects. No, I'm sorry, I'm confused. If you take, okay, go ahead. What is your argument here?
Right.
That's a cross term. That's not the actual thing itself. I'm confused.
Sorry, what's a cross term?
Look, if what you're doing is you're trying to compute, given a particular psi, you're saying you project it onto some basis.
Right.
And that's okay. And you're taking that projection onto that basis. Okay, go ahead. So now what?
Right. So then, so those two geodesics will have path weights associated with them on each vertex.
Yes.
So when we construct the string diagram, and you consider what is the path weighting of all of the paths in that string diagram, because you're doing a shortest path computation from each vertex on one to each vertex on the other, what you're actually doing is multiplying path weights.
I understand that construction. Now let me understand why that has anything to do with anything. Okay, so what you're saying is, forget about the whole geodesic. Just look at the end point, right? At the end point, you're trying to get from one to the other.
Uh-huh.
But why are you computing? Okay, so the path weights, I'm really confused. So the path weights for the geodesic that goes, oh, I see. The geodesics from one of these, to get from one of these geodesics to the other, you are essentially filling in this whole rectangle.
Yes, right.
Okay.
Because you're constructing a plane, and the point is the aggregate path weight of that plane is the product of the path weights on the two geodesics.
That might be true, but let me just understand. So okay, so what? Why is it relevant what the path weight of the plane is?
Because then that's the outcome of your classical measurement. Or if we then interpret that as a completion, right? Each one of those relations mapping from a point on one geodesic to a point on the other geodesic is a completion rule. So this projection you can interpret purely as a completion procedure. So then if you want to know what is the path weighting of the completion step that you have to do, it's telling you that in order to obtain that, you're simply multiplying the amplitudes associated with the two geodesics.
Okay, let me understand the claim here. So the claim is that to make a measurement that says that psi is aligned with some basis, mm-hmm. you have to do a completion, have to do all the necessary completions to basically conflate psi with that basis.
Right.
Okay. And now the question is, when you do that, when you conflate psi with the basis, how much other stuff are you entraining? How many other path weights are you entraining when you conflate psi with the basis?
Exactly.
Okay, so the claim is, okay, so imagine you have
which I think, by the way, is the same as your interpretation that you were giving earlier, but it's a more geometrical way of thinking about it.
Well, let's go through both of these, okay? Imagine you have some quantum path, i.e. a geodesic in the multiway system. Okay, so now imagine you have a basis path, right? Now the question is, if you do a measurement, I still need to completely wrap my head around this idea. If you do a measurement, if you do a measurement which leads to that basis, which leads to you measuring that basis, concluding you're in that, you are in that basis state. you need to do enough completions to conflate the two JD6, right?
Mm-hmm.
i.e., okay, so, and the claim is, okay, so as we make that string figure, we are, every point on one of these JD6 has a certain path weight going to it. I need to make a picture. I mean, so taking the naive thing, let's say we have a grid and you've got two lines in the grid, right? And you're going to stringly align those two lines. You're asking the question, now I'm a little confused here. Do you see what I'm saying? If we have one of those, grids at 45 degrees, if we have a multi-way graph that's just a grid at 45 degrees, okay, like the BA goes to AB.
Yep.
Right? So let's consider BA goes to AB. So walk me through how this works in that case.
I don't have anything more to say than.
Well, let's just look at it. Let's just look at the actual thing. So we've got a all right, here's our grid. Okay, so what you're imagining is, so tell me where is a basis state here? You're
Well,
saying
any of them can be interpreted as basis states.
Okay, but maybe we should have a
basis.
convenient one. Let's just
We'll pick the rightmost one, the rightmost geodesic if you want.
Okay, all right, fine.
And then project onto the leftmost.
Okay, so there's our rightmost geodesic. Okay, so now we say, I'm going to measure, let's say, this geodesic here. And I'm projecting that onto the rightmost thing. Okay, so that means I'm doing completions that lead that one onto the rightmost geodesic.
Uh-huh.
So, okay, so that's effectively taking those edges Okay, the claim is then that as I do that conflation, that whatever path weight was coming in is spread over all those paths in the rectangle. And therefore, I get, when I conflate it, I get all the paths from that rectangle contributing to my measurement value, right?
Mm-hmm.
Okay, because if we want a single size squared, I still don't quite get it. If we have I understand with this projection that we're looking at the product, let's think. We've got those two things. No, I'm sorry, I still don't get it. Okay, walk me through this again. So we've got a path weight coming in for this JD6 here, right? Got another path weight for this JD6 here, let's say, right?
Right.
Which they came from completely different places. They have completely different path weights.
Mm-hmm.
Okay, so now we want to look at were we to conflate those GD6, how would that aggregate the path weights, right?
Right.
So explain to me why. So let's say this has a path weight of A, this has a path weight of B, X, Y, no, let's call them X and Y, path weights of X and Y coming into these two GD6.
Nice. Yep.
Okay, now what?
Right. So obviously that's indicating that there are X different possible evolution trajectories which lead to the thing on the left, and Y possible evolution trajectories that lead to the thing on the right.
Yes.
Right. So then if you take, so morally, there are therefore X times Y different branch pairs. Because for each thing on the right, there are X different evolution trajectories that go to the left.
Yes.
Right. So there are overall X times Y different branch pairs. So if you wanted to construct the full completion, you would need to have a completion rule whose path weight itself was X times Y, or 2 times X times Y, depending on how you do it.
What do you mean the path weight of the completion? I don't understand that.
The completion is the projection, right? So it
Yes.
itself is a geodesic. It will also have a path weight. Its path weight is X times Y for the reason I just stated.
Well, the completion is an aggregation of many of these individual, the big completion that you need to get one of these geodesics into the other is a sort of bundle of other individual branchial edges. And your claim is that that bundle has to contain, okay, fine. So that bundle contains X times Y individual branchial edges in the bundle. Okay, so now, so what?
Right. So then, given that we have this preservation of measure, and so given that we have, in particular, these weights are normalized so that they always sum to 1. And so when we have performed a measurement operation, when we've performed a projection, we can interpret those weights as corresponding to probabilities, even though when they are thought of as being weights on individual GD6, we interpret them as being magnitudes of amplitudes. And the Born rule, of course, is the thing that says that the magnitude of the amplitude and the probability are related by multiplication.
Well, by squaring the magnitude in particular.
In conventional quantum mechanics, yes. But our formulation implies you can't project a geodesic onto itself. You have to project it onto a geodesic that's separated infinitesimally. Yeah,
fair enough. Okay. Well, so that's the limit then that causes. Okay, so then, but then, what? I still don't understand why we get psi squared. Why we're not getting? Why the distance between GD6 isn't sort of the other side of the rectangle, so to speak? You're arguing that. Go ahead.
No, sorry, I don't understand the question.
If you have two very close GD6, you have this infinitesimally separated GD6.
Yep.
Because basically you got a basis state.
Yes. Right.
Okay.
So imagine they're so close that they both have path weight X. Right.
Yes.
Then the weight of the completion geodesics is X squared.
Okay, let's go through that. I don't understand that. So let's take the two things that are this one here and this one here. Okay?
Yep.
Okay. So in what sense is the completion GD6? So those things both have path weight X coming into them.
Yeah.
Okay. Explain why.
So let's go to the final state on both, because that's ultimately the one that actually matters.
Yes.
Right. So if they both have path weight X, then for each evolution path that takes you to the final state on one, you get X on the other side. So there are a total of X squared branch pairs.
Okay, hold on. So I don't completely understand this. So the ladder, no, I don't get it. If you just have this ladder, it's going between two path weight X states. And it's going back and forth between two pathway X states. But why isn't it just, why are there X squared completions there?
Well, you
Why
have to work out what is the actual path weight of the completion, of the completion geodesic.
Yes.
Right? And so the way that our code does it, and the way that I think it should do it, is it counts the number of branch pairs. There's one completion, or there's two completions rules for each branch pair, right?
So you're saying if I were to do path weights here, if I were to say, is there a way of showing path weights on this? Yes.
Yeah, include state path weights. Goes to true. And then you could say vertex labels arrow vertex weight.
What is it?
And then arrow, I think it's string vertex weight.
Okay.
There we go.
All right. Oh, this is useful. Okay. So now, what are you trying to tell me? So this is accumulating path weights down that geodesic there.
Mm-hmm.
And something else is accumulating path weights as well. But so now how do I understand what's going on here? Maybe we need a slightly larger, go ahead.
I don't understand
just walk me through the computation, right? So we've got this geodesic here, and we've got its path weights, right?
Right.
We've got a geodesic, let's say the geodesic all the way over on the right here.
Yep.
Okay. So now the question is, if I'm trying to project one geodesic onto the other,
yep,
how do I do that? And how do I assign path weights to that projection?
Mm-hmm.
Okay.
Yep.
So let's go through that for this case.
Yeah.
Right. What you're saying is every branch pair is crushed, right? Every intervening branch pair between this thing and this thing is getting crushed out by a completion, correct?
Right.
Okay, so every one of those branch pairs that has, let's say that branch pair there, that has a 2 coming into it, is now another geodesic going, that defines another. Okay, can we actually do the completion here?
Yeah, of course we can. But we're not doing the completion at that level. We're doing the completion at that final time step, right? You've constructed a hypersurface which has the BAA-ABB state and the AABABB state as being simultaneous, right?
Okay.
So we're not constructing the completion up there. We're constructing the completion at the place where you said, aren't we?
Yeah. Okay. Down here.
Right.
So okay. So then let's add that completion in to our rules here. Okay, so let's put that in here. Let's say, what is it? AA, BBAB goes to AB, AA, BB, right?
Did
I get it wrong?
I'm confused. There's a different state to the ones we. Oh, you want those two to be simultaneous?
Well, which ones would you like? Just pick your states.
Well, if those are the two, then you should remove the third. Then you should remove the fourth A from the second, from the right hand side.
The fourth A. I mistyped it there.
Yeah.
Okay, great. Okay, now how do I interpret this?
I mean, I still don't really understand what you're doing.
Well, I don't know what I'm doing either, but you're trying to tell me how I end up getting multiplied path weights when I've done this completion. That's what I'm trying to see. Mm-hmm. How do I, in this picture, right, there should be a way to see that the path weights get multiplied, right?
Yes.
Okay, so where are those multiplied path weights?
But it's not in that picture. Obviously, we have to define what the completion procedure actually means first. And all I'm saying is we do a single completion step for each branch pair, in which case there are X times Y branch pairs, so there are X times Y completion steps.
Okay, but were we to do that in this picture, your claim would be, right? Were we to do that in this particular picture, we're just to add a bunch of completions, right?
Mm-hmm.
Then these path weights would actually turn into, it would just be something where this diagram gets kind of squashed by the fact that it has a lot more causal edges and a lot fewer intermediate states because they all got completed out.
Mm-hmm.
Okay? And so its path weights in that aggregated picture will be uninteresting. There'll just be one most places. So I'm trying to understand in what sense the path weights get multiplied.
In the sense that you add X times Y, you perform X times Y completion steps.
Okay, but look, okay, so you're saying that in addition to counting path weights in this actual diagram, we count the act of a completion as, but I mean, we should see that here, right? Because we've got an edge that right there, that is the edge associated with that new kind of event, right? Actually,
yeah,
it's not that edge.
But those two states were about to converge anyway. So this is a completion that doesn't do anything, which is why I'm confused as to what we're doing.
All right. Okay. So fine. So tell me what. Okay. Let's go back to this picture, right? And let's add the completions that are needed to project onto this right-hand side. So you're saying that to get, let's say, this state onto that state there, right? Okay, so let's look at what's needed to do that, right? The minimal completion needed to do that. Is there a way of asking to compute that?
No, because we can just work it out. If you know the two states that you want to deem as equivalent, you can just deem them as equivalent. Right?
All right, fine. So let's do that. So let's add, okay, these ones, I thought these were the ones we were doing anyway. Weren't they those two?
Yeah, I thought they were the ones you were doing. And then you picked two that converged after one step, which is why I got
wait. Okay, so I did the wrong thing. Okay, so A, B, 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 A. Okay, B, A, B, B. Did I get that right? B, unfortunately, I have the way I have this set up. Oh, that's triple A, B, B. All right, so where is the product? A, B, 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 A. That's the unusual step there. That's the completion right there.
Uh-huh.
Okay, so you're saying B, A, B, B.
Okay, so do you mind if I share for a moment?
Go ahead.
Okay, because I think it's useful to do this with an example where the measurement actually means something, i.e. where you don't have immediate causal invariance.
Yeah, go ahead.
So, okay, hang on. Can you see?
Yep.
This is my trivial example of a non-causal invariant system. Okay, so if we have, let's do this for 3 steps or something. Okay, so if we have triple X, triple Y, these are the two states we want to complete. They both have path weight 2.
Yep.
So then if we add that completion step, Y, X, this is a single step completion, so we can just run for one additional step, and you'll see that this now has weight 4.
Which has weight 4?
Those two objects.
Can you make a layered? Can you make that a layered plot? Just.
Yep.
Make it. Oops.
There you go.
can change the. All right, let me understand this now. So why did I see? So that got the contribution, that path weight contribution of YYY was delivered from both sides.
Right.
Wait a minute, without the completion, that would have just had a 1 there, is that correct?
That would have
sides.
That would have had a 2 on both sides.
Why?
Because those two things had path weight 2.
Can you show all edges, not just the edges? How do you show all the edges? Because that had 2 different. The YY has 2 different rewrites that lead to YYY, right?
Yes, right. It would be. I think that's evolution graph full or evolution graph.
I think that's right. Okay, there we go. That's much better. Okay, now the problem is that we have not conflated the xxx's, but were we to conflate those, we would have 2 plus 2 there, right?
Right.
The 2 xxx's. Okay, so now run this, take the exact same thing, run it for one more step. Okay, so now, how many xxx's are there in this picture? There are 3 xxx's, right?
Right. Looks like it.
Okay, so then the total path weight of xxx is 3 times 2. So how do we understand that? How does that relate to your multiplication story?
Well, that's now saying that I don't have an immediate. I mean, we've already performed the measurement. I mean, we're now looking at things after the evolution after the measurement has been performed. I'm not aware of an interpretation of the Born rule that gives you that.
All right. Okay. So go back then. Go back again.
So sorry.
Go back to 4 again. Go back to 4 steps.
Yep.
Okay. Let's admire this object here. So I don't understand this object. So that there were time-like. What am I counting here?
Look. So here's my point. So there are how many? If we consider all branch pairs that exist at this time step, what are they? Well, they all have the form xxx, yyy if you get rid of the trivial ones, right? The point is there are 2 different ways for you to get to xxx and 2 different ways for you to get to yyy. That makes 4 total branch pairs.
Yes.
So those are 4 independent paths along which you have to traverse if you want to make a completion step.
Okay, let me see if I understand that. So your claim is these branch pairs, which might involve some of the same edges, but you're simply asking combinatorially, what are the things that are branched from each other,
right, that
you need to unbranch?
Right. And so for a pair of events that exist on a single branch-like hypersurface, that is the product of their path weights. Hold on.
I see. So your claim is that a branch pair can be fed.
This is why in the branch pairs function we have include duplicates true false, right? Most
Why
of
don't
the
you
time
run
you don't
that for this case? I mean, in
yeah.
other words, so you're saying the Born rule is the story of include duplicates in the branch pairs.
Exactly. Let's do a, I don't know.
Let me think about this for a second. So you're saying for every path, if they're X and Y paths, I mean, for every path, I think maybe include, I have to look it up.
Does it give duplicates?
No, just look it up. Just click the multi-way system icon there. Click the multi-way system icon, you'll go to the documentation.
Yeah, no, sorry, it's okay. I'm bringing up the documentation now. Look. Does an include self-pairs include full branchial space? Did I not include? There was definitely a version of this code where I had an option to include duplicates.
No, you do. But maybe it's different from branch pairs list. Maybe it's called. Are you sure the branch pairs list doesn't include duplicates? Yes, it doesn't. So is there a full branch pairs list or something?
It doesn't appear to. I mean, if nothing else, we could do an include. We could uglily do an include state IDs.
Okay, well then all you have to do is for each thing there, get rid of its state IDs.
Right. We can just do a last mapped at level something.
Map last at probably level 2. Brace 2.
Yeah, sorry. Yep.
Okay. All right, so now do a counts on that.
Right. Okay. So if we consider this branch pair here, it's got a.
Which branch pair?
I don't know. Let's do the one up here, for instance. Or
why don't you just do a 2-step evolution then instead of a 4-step evolution?
That's a good point.
Okay, now compute that for 2 steps.
Okay, let's do. Yeah. So let's take that and that.
Okay, so X, all X's, and X, Y, Y, X. It's down. No, where is it? Oh, yeah, it's the second one on the last row. Second one on the last row has path weight 2. I mean, there are 2 branch pairs. I don't understand that.
But then X. YYX.
Look, I get your point that if you've delivered 2 things, I don't think this is the right computation. What you're doing here is not the right computation. I think what you need to do is go another step here. Go one more step, 3 there, okay? And then pick out the XXX, pick out that thing there, which I see as path weight 3. That's crazy. The 3 branch pairs for XXX, XYYX. Okay, go another step, and then take, okay, go another step, and now extract from that. Just take a key. Just take the XYYY. You get what I'm saying? XXX.
Right.
just as a key out from the counts. Yeah, percent. You just say percent. All you have to do is, because the counts,
Sorry,
they're the keys of the counts. X,
and
Y, Y, X.
But don't we also want the reverse?
We might, yes. Okay, so that's 3.
But then if we also did,
well, if we did a key map, oh, go ahead. All right, whatever.
Let me do it hackily. 6 and 3.
I don't think you've got your percent right. Percent 897. Just say percent 897. Okay, percent 897, and then do a list in this. Oh no, you can't do that. Never mind. Go ahead. Yeah, go ahead. Go ahead. That's odd.
Wait, is that
Maybe
right?
the branch pairs are getting sorted. Run it one more step. And let's just name that thing.
But this is a strictly growing system. It's not, this won't add anything.
Yeah, okay, fine. Fine.
I'm wondering, am I doing something stupid here? Let me just see if I do that. Okay.
Same result, 6 and 2.
Ah. No. Okay, this is doing the right thing. My thinking is just wrong. Because what we're really asking, yeah, right. Branch pairs list is only talking about one-step branch pairs. But what we really care about are multi-step branch pairs, right? Because when we say that this has path weight 6 and path weight 2, what we're really saying is, from the start, there are 6 ways to get here and 2 ways to get here.
Yes.
And so what we really want is some branch pairs list that takes branch pairs not just a single step back in time, so to speak, but actually right to the beginning. Because this is actually right, the 3, right? Because you can see there are just 3 evolution edges here and 1 evolution edge there. So there are 3 independent branch pairs. But if we took the branch pairs from the start, there would be 6 going here and 2 going here, and then you get 12. But that doesn't exist.
Okay, so hold on.
Which means we can, but I can test this hypothesis because I can just do, if I do something like this, let's do something a bit more interesting. So how can I get something else that has different weight?
Well, by having 2 initial conditions there. That will give you different weights, right?
Yeah, but then they'll come from different places.
All right, okay.
They won't be branch pairs. So I need something that's going to.
Well, an XX goes to something. XX
if I just add another rule like this. Oh yeah, okay, that changes it. So then what I'm thinking is, if we do that, one step. Oh, XXX. There we go, 6. XXX, XYYX. Wait. XXX, XXY has weight 6.
And what about XYYX? I'm not seeing that one. I don't even see. Oh yeah, that's 5. 5. Look at that. XYYX quadruple X is 5.
Oh no. But then the reverse has weight 1.
Really?
Look, you can see here.
Oh yeah.
That one there, this one there, and then like here we have 3 and 3.
Okay, so let's walk.
They all have the right. This is correct.
Okay, so let's walk through this again. So what's happening is, from the root, the way we should think about it is, okay, here's how we think about it. These are pairwise path weights. Make your picture again for 2 steps, okay? Take out your extra, make a separate line because we don't want to lose this one. Okay, so take that guy.
Okay, do you want me to remove this stupid degenerate rule?
Yeah, I want you to remove that rule and then make it 2 steps, but put it underneath. Put it underneath the thing you did before, because otherwise it's going to confuse us. Put that whole thing. No, just
Yep.
just copy the cell. Yeah, right there. Okay.
Oh, sorry. What did I do? Two
No,
steps.
just have double commas there. So right. Okay. So now my claim is that what you need to think about is, instead of the single path weight, so you are going to 2 different places down at the bottom there, right?
Mhm.
So the question is, what are all of the paths that lead to that bucket of stuff? And that set of paths is obviously the product,
Yeah.
right? Of,
Right.
okay, so hold on, let's just walk this through
And
again.
I think this would be easier to understand if I added an extension to branch pairs and everything that allowed for arbitrary width, so to speak, arbitrary time-like width.
Yeah, no, I agree, the multi-ancestral branch pairs.
Right.
But in this case, what we're saying is, if we're looking at the path weights, we're looking at the joint path weights, right? What are all the double paths to get to these 2 outcomes, right? And clearly the number of double paths is the product of the number of paths to get to one of those outcomes. I think is that obviously true?
Yeah.
I think so, yes. Because at every stage, you are either taking, it's not completely obvious to me, but I think it's true. And
No,
what happens if there's some
it
kind
is.
of,
It's definitely true.
so long as you can get to both of them.
Well, they're a branch pair, so you can.
Well, I understand that, but those, okay, so you're saying, given 2 states, but if you just pick 2 arbitrary states down there, they might not be related. In the particular multi-way system you're looking at, if they didn't start from the beginning of the universe, they might not be related.
Right.
If they are related, then the product, then to get to both of those states, aka to get to a completion, I mean, so we're going to conflate those states by a completion. And we're going to ask, what is the total of that coarse-grained completed state? What is the path weight to get to the completed state? And that's the product of the path weights of the individual states.
Yep.
Do you agree?
Yep.
Okay, so now, let me think about what that means. So that's telling us, okay, so now we're making the claim that measurement consists of conflating, so think about it in multispace. In multispace, measurement is the conflating of the sort of branchial tower by virtue of coarse graining. So you're doing that here, and you're asking, what is the aggregate path weight of the coarse-grained object? And the claim is that if you are projecting one state onto another, that the aggregate path weight, okay, I believe this. The aggregate path weight is the product of their path weights.
Mhm.
Okay, now let's talk about psi squared. Okay, for an individual state, the self conflation.
Right. Well, I mean, if we really want to get meta, that's just the case of include self pairs goes to true.
Let me understand that. So self pairs means, what is a self pair? A self pair is the thing that is, I don't understand the self pairs. Self pairs, isn't self pairs multiple rewrites of a single thing?
Yeah. So like here, you can see that because this has path weight 3, there would be
Well,
3
now, okay, wait a
separate
minute.
self pairs, right?
Okay, can we do this, include self pairs?
Yeah.
You just did that, okay. So now, what are you saying? So you're saying XXX, yes, there are 3 self pairs there.
Right.
Okay, so let me understand that. So, but without the self pairs, I don't understand. The path weights, but it has some path weight without self pairs, right? It has path weight 3. Quadruple X has path weight 3, let's say, right?
Uh-huh.
So why does self pairs? I don't understand. Is self pairs squaring something? I don't see it.
No, I don't think it is. Which is why I was saying I don't think that you can actually perform a perfect projection measurement of a state onto itself.
All right, so let's understand that from so you're saying as soon as, see, that's a little weird because in ordinary quantum mechanics,
measurements are instantaneous projections, but our formalism predicts that they're neither instantaneous nor perfect projections.
Let me think about that for a second. See, maybe it's a fiction that psi, I mean, like a Schrodinger, in the Schrodinger equation, a position basis. You're saying that we really have to pull it apart. We have to say, it's a little odd. See, what's odd to me is that something instantaneously close, or infinitesimally close, Well, the claim would be measurement is comparison in some way, or projection, whatever you call it, that there is a projection involved.
Mm-hmm.
And the self-projection is somehow a fiction. Okay, so let's walk through this one more time. So the claim is that the quantum amplitude is given by, the magnitude is given by the path weight. The phase is given by the position in branch-Hill space. Now we're going to do a measurement. And that measurement consists in projecting that, asking the question. Okay, so we have to make the claim that an individual quantum state is not observable. It has a magnitude and a phase, it's a happy creature, and when it comes to adding up quantum, if we want to combine, if in our measurement we are, so let's walk through this. In our measurement, we're saying we're adding up 2 quantum states and then projecting them for our measurement. So the very act of adding them up, if they're on the opposite sides of branch-Hill space, has already lost. We couldn't get them both into our same measurement in some sense. Because our measurement is an attempt to project into something which is somehow nearby in branch-Hill space.
Yeah, the interference comes at the level of the projection.
Well, I'm not sure that's the only way to say it, because what we're saying is the measurement is a projection onto some fiducial path in the multi-way graph.
Of course.
Basically, right? Okay, so then what we're saying is, let's see, if we're attempting to project 2, we're first of all, we're saying we're projecting both states and they're on opposite sides of branch-Hill space. I'm a little bit confused here. Okay, so no, I'm still confused. Okay, let's think about this, the 2 things. So we've thought about adding together those 2 quantum amplitudes, right? Yes, I see the point. I see the point. Okay, so look. The issue is there's two different things. There's magnitudes and there's phases. If the two things are very nearby, it will be correctly the case that to find their joint, sort of joint probability, it's just a matter of path weights. But if they're far away in branch hill space, there's more to it.
Of course, because phase is a measure of the branchial separation as a ratio of spatial separation.
I understand, but so let's just walk through what's involved. So let's say
so if you have pure branchial separation and no spatial separation, you get perfectly destructive interference for the same reason we discussed before. That corresponds to the case in which the geodesics are orthonormal, or are orthogonal, not orthonormal.
Okay, hold on.
If you have perfect branch-like separation and no spatial-like separation, you get destructive interference, as we discussed before, right? Because of the multi-space projecting from the top of a tower idea, right?
No, I understand. That
right.
claim.
And so because phase is a measure of the ratio of branch-like to space-like separation distance, that case where you get perfect destructive interference is the case where you have a maximum phase difference, where you have.
I understand. Where the thing is just going off in the branch hill direction, and it doesn't have any.
That corresponds to orthogonal geodesics, where any projection you make necessarily destroys all information.
Let's walk through that again. I think that's basically right, but let's just walk through that again. So if we were to draw this picture in multi-space, okay? So the bottom of this picture is right now laid out in some vague approximation of branch hill space. Right? But we could lay it out in multi-space. And were we to do that, you're saying...
The higher the elevation, the greater the phase difference.
Right. But so that means... Okay, hold on. So when we make a measurement, we are coarse graining to attempt to remove branch hill data. But so one of the things in multi-space is there is path weighting. In other words, multi-space should be weighted. Multi-space is not like our ordinary hypergraph, which is an unweighted hypergraph. The claim is that multi-space gets weightings just like, as its branch hill direction, okay? In the individual sort of nodes in the branch hill direction, there are path weights just like there are on these states here. There are path weights on the local states just like there are path weights on these global states.
Right.
So what that's saying is, so in multi-space, things are weighted. And so this Born rule thing, okay, when you do a projection, the claim is, when you do a projection and the phases line up, it is merely a question of multiplying the weights. That's the claim, right? When the phases don't line up, there's more you have to do. Is that
right? I mean, the outcome state will always have the additive path counting thing, because that's just the combinatorial structure of measurement. The point is that the further away in, the greater the phase, the more information you're losing in the process of doing the completion.
How does that translate to a smaller value of the amplitude of the probability?
Because if you think about each global state can have an additive path weight. But if you look at the individual substates, like be it substrings or subgraphs or something, their path weights can go down as a consequence of the completion procedure losing information.
I think that's qualitatively correct. It would be nice to see, the question is, can we make a local multi-way system effectively in strings and see that very explicitly?
Why do you need a local multi-way system?
Because that's how you're going to see this thing about having that's how you're going to see for the substrings. I mean, you're talking about for the complete state, you're talking about what happens to the weights of the substrings.
Yeah. Well,
it's just a convenient way to do it. I mean, you could do it, you could deduce it from this by just aggregating together. You just make patterns for these things. You just aggregate together those states which agree on some, you require the states to agree over some range and then to be different over some other piece. And it's like a completion, actually. What is the analogy between a completion? Oh boy, this is getting too complicated for me. Okay.
All I'm saying is exactly the same thing that as I brought up several times in that quantum computing discussion, right? That if you apply completion procedure to this, you're going to end up with something like that. Whereas if you apply completion procedure to this, you're going to end up with something like this, right?
Wait. What's the right-hand side? The right-hand side is
the outcome of the completion.
What do you mean? It's not the same data type. What do you mean by the completion? Oh, you mean the completion of, I see. In order to get.
What is the most general unifier of these, or the most general resolvent of these expressions, right?
Yeah, but I'm sorry. What do the ones and minus ones now represent?
These are just vectors. I mean, I mean, we could do it with strings.
But the qualitative way to think about this, right, is that the 1 minus 1 in that second case in multispace, that's a tower in multispace, whereas in the first case, they're just two different points at different spatial positions, right?
Yeah, of course. This is pure space-like separation. This is pure branch-like separation. So yeah, of course, this is horizontal separation, vertical separation in multispace.
Okay.
Right. So obviously the path counts don't matter. The path counts are the same in both cases. It's the question of what information you're preserving and what information you're destroying.
Let's see that in an explicit thing with strings. So you're saying that the basic point is, in that second case,
I'm not saying anything. I'm not saying anything new. I'm not saying anything new.
No, I know you're not saying anything new. I know you're not saying anything new. I'm simply trying to understand it properly. And what you're saying is that in the second case, you're basically requiring the conflation of everything in branch Hill space, everything at every position in branch Hill space.
Sure, yeah.
In order to get those two things, in order to get from one to the other, you have to sort of span the whole of branch Hill space.
Mm-hmm.
Therefore, there is, insofar as information is segregated in branch Hill space, you just crushed all of it out.
Right.
So another way to think about this is in
Oh, yeah, that's what was going on.
I think the basic intuition, again, is, see, the thing that's bugging me is, why do you always have to project? You're always computing.
That was incredibly boring.
Okay, listen, look. Here's the confusing thing for me. Okay, you've got these two. What you're doing is you're getting psi1 plus psi2, and you're measuring that whole thing, right? What's confusing to me is the difference between the plus and the measurement projection operation. Did that make sense? Because what you're
really.
saying.
What is psi1 plus psi2?
Okay, so you're saying there are these two outcomes that you are considering. There's two quantum states that you are considering, and you are measuring the superposition of those, right? The superposition is this thing where you have two points in branch Hill space. And what you're trying to do, what's that?
Is that what we're doing?
Doing what?
What does it mean to measure the superposition?
Well, we're trying to find, for that superposition, we're trying to find psi1 plus psi2 squared, basically.
But why are we adding anything? Why aren't we just taking psi squared?
Because psi is equal to psi1 plus psi2.
But why can't we just measure a pure eigenstate? Why do we have to measure a superposition of two eigenstates? I thought we were only...
Well, because that's what interference, that's what we get. That's how we get interference.
But you can also get interference from the thing against which you project the eigenstate.
I understand, but if we've got two different paths, okay, look, the different intuition is, here's another intuition for interference, okay? You've got two, in the path integral, basically, in the paths that you're following, you've got two different paths that you could follow. Oh, I'm confused. Well, the claim I'm going to make is all right, you're trying to measure, the photon at this position on the screen or whatever. There are two paths that could lead you there. No, I'm really confused. Okay, do you want to try your explanation again?
If I can understand the question, then I can.
Okay, so the question is this. Okay, so an interpretation here is the probability to measure a particular thing, to measure a particular is you take your sort of fiducial measurement path, which might be something to do with an observer. Okay, you've got your fiducial measurement path and you're asking the question, what is the joint path weight of the fiducial measurement path and the thing you're trying to measure? Okay? And assuming that the phases line up, that's basically the product of the path weights.
Yep.
Okay, now I want to consider the next case. The next case is I've got two possible things that could happen. Something should go through slit 1 or slit 2.
Yep.
Okay. But then I'm going to do a measurement on the result, but it could go through slit 1 or slit 2.
Mm-hmm.
So should I think about that as three things going on? I've got the slit 1 path, the slit 2 path, and the path that's just associated with the history of essentially the thing on the measurement screen.
You can do, yeah.
Okay, then I'm asking, what is the path weight associated with I see.
Right, because the point is that in the double slit case, right, you have there are two geodesics against which you are measuring. The geodesic along which the particle definitely went through the left slit and the geodesic along which it definitely went through the right slit. Then you take the actual geodesics and you project them against those two things. And then that gives you a product of amplitudes that you then interpret as the probabilities of it going through the left and right slits respectively.
Well, but a different thing is, imagine that I'm looking at the destructive interference in the middle.
Sure.
Okay, then what I'm doing is I'm asking, then the reason that that doesn't work is because both through the left slit and through the right slit, let's see, there's no place where both geodesics end up in the same phase in branch hill space effectively. So wherever I'm trying to project to, I really lost the game because those two geodesics are already, but if the geodesics are very close together, I see, it's the sum of the path weights. Wait a minute. Why is it the joint? Okay, so one of them is just asking, oh boy, what's the difference? Okay, so the final thing, why are you projecting? So that means I think I get it. I think I get it. So basically the path integral effectively is just adding up path weights. It's not multiplying path weights, it's adding path weights.
Mm-hmm.
Adding path weights together with trying to figure out whether the target, so to speak. I mean, basically the way I'm thinking about it is, okay, here's the way to think about it. Okay, you've got your fiducial geodesic that is the basis vector that you are measuring against, that
Yep.
you're projecting against. Okay.
Right.
The basis geodesic is going in a certain direction. Okay.
Right.
Question one: how much of the path weight of the geodesics that you can, of the actual process, actually hit that target area? If they're both going bonkers, they go nowhere near that target area, you know, you can project as much as you want. It's not going. It's just not. There's no support for that, right? There's nothing. It's zero basically.
Mm-hmm.
Okay, so assume that the two JD6 landed in your target area. Now you're asking the question, I see. I think I see. Okay, you've got the two collection, basically your two interfering paths, effectively, or your two psi1 and psi2, right? They contribute all their subpaths additively.
Yep.
Which then get multiplied into the path weight of the fiducial path, so to speak. I don't quite get this. So, okay, so that means, again, why does that, and so if the fiducial path agreed, if the fiducial path, okay, the fiducial path is a different path, but with essentially the same phase, the same target area. And you're saying, what are you saying? You're saying that to classicalize what's going on, all right, let's try this again. In multispace, the different, what's happening is the different paths of the photon or whatever landed up in different places in that branchial tower. Okay?
Yep.
Now your measurement picks out a certain place in the branchial tower. And then the process of doing the measurement requires completion.
Right. Yeah. Obviously, your measurement is just picking out a surface in multi-space and then projecting onto that surface.
A surface in that has a certain height in branchial, for any given spatial position, has a certain height in branchial space.
Yes.
Okay, but why is that projection?
So you could project on. Sorry, go on.
Go ahead. Why is there a product? Go on.
Yeah, so obviously you could project onto the surface where the thing goes through the left or goes through the right or something in between.
For sure.
Right. And it's
why is there a product of those things? Because remember that what we're doing in multispace now, every point in multispace has a weight.
Yep.
Both the measurement surface has a weight and the outcomes have weights.
Mm-hmm.
Okay, why are you multiplying the weight of the measurement surface?
I mean, other than the explanation we already went through, I don't have an alternative.
I understand, but so what you're doing is you're trying to. If you think about it in multispace, you've got this. You're trying to fill in this web, this string figure.
Yeah. Every point on your measurement surface and every point that on the thing that you're attempting to measure has an associated weight. And for each unit element of weight on one, you have to draw a path connecting to a unit element of weight on the other. So it's naturally multiplicative.
Let's put that a different way. So the issue is you're trying to...
Which, by the way, explains why quantum evolution is linear and measurement is nonlinear. It's the distinction between additive and multiplicative identities on path weights.
Okay, let's walk through this one more time. Okay, so what is the relationship between the observer and the fiducial path?
Well, the fiducial path is the thing which the observer thinks happened and is trying to determine whether it's actually true.
Indeed. So, but that the fiducial path might actually be thought of. So what the observer is trying to do is they're trying to say every branch pair that made what actually happened differ from the fiducial path is a fiction.
Yeah, we're going to mod out by all of those.
Right. And the number of those that have to be modded out by, because, okay, here's another way to think about it. The observer might think that their fiducial path is just one path, but it's not. It's a whole bundle of paths, right?
Right.
With non-unit path weight, because it's a whole bundle of paths
Mm-hmm.
that happen to be, well, that might happen to be identical, spatially identical, so to speak, or might not be. It doesn't really matter.
Mm-hmm.
There's a bundle of paths that correspond to the fiducial path.
Right. And so for each elementary path in the observer and each elementary path in the thing they're observing, there is a completion path.
Okay, so why is that? I mean, there are tons and tons of completion paths that need to be followed.
Yep. But most of them will be the same. So we can think of them as just being one completion path with a certain weight. And that weight is the product.
Right, because it could be any thread of the observer together with any thread of what they're observing.
Of the system, yeah, exactly. Exactly.
Okay, so hold on. So that means that the path weight of this circumstance of the observer aligning themselves with the observed system. That's what I'm not quite getting. I don't understand the fact that you have to add so many completions. I don't understand why that contributes probability, so to speak, to what's happening. In other words, you're saying every thread of the observer has to be aligned with every thread of the observee.
Mm-hmm.
But what we're trying to explain is why the observer imagines there to be a certain probability. Oh, I think I see.
I mean, it's just because we're normalizing the measure, right?
Yeah. So
You have you think of all the completions that that exist in the multi-way system. We normalize all of the ones that occur on a particular branch like hypersurface so that their sum is 1. So the fraction of your completion that corresponds to this measurement, the fraction of the total completion that corresponds to this measurement is therefore interpreted as a probability.
Okay, let's walk through this again, okay? The observer, AKA the observer's fiducial path on this basis, right, is a thread, is a collection of threads, okay? in principle, those threads read against every thread in the universe. Right? But we're asking, of all the things that could happen in the universe, how many ways could something that corresponds to this quantum process have happened? So that's asking, no, still don't quite get it. So in other words, this particular quantum process has some threads that are operating, and you're asking the question, no, I don't quite get it. I'm sorry, I don't quite get it. So you've got this quantum process that's happening. You've got 3 different choices of quantum process that are happening, might be happening, right? Each one has certain threads associated with it. Why are you multiplying? So hold on a second. Why do you... Wait a minute. So the observer is just doing their thing, whatever it is. And they have a certain pathway associated with doing that thing. Now along comes something else, and it's do you see what I'm confused about?
Not really. What?
Okay.
What's the question?
Okay. All right. So we've got an observer. We've got this fiducial path. It is a collection of threads in the multi-way system.
Yep.
Okay. We've got 3 different quantum things that could happen. Each one of those is a collection of threads in the multi-way system.
Yep.
Okay. The question is, the observer is trying to figure out which of these happened and with what probability.
Yep.
Right? Okay. What does the observer do? Or how does the observer think about that? So I see. So the question is, what's the alignment, the projection of each of those things onto the threads that correspond to the observer's fiducial path?
Right.
And the claim is that to measure that projection, you look at the area, effectively, of this piece of webbing. I don't quite get that.
Because then as you follow the observer's fiducial path, you can ask what's the total contribution as a fraction of the path weight to their state in the future from each of the 3 possible quantum evolutions, and that will be given by their respective products of amplitudes.
All right, let's understand that for a second. Okay, so you're saying to the observer's future, right? The observer
has many possible futures associated with the many possible quantum evolutions of the thing they're observing. Right?
Okay.
So there's a future in which they observe A, there's a future in which they observe B, and a future in which they observe C.
Mm-hmm.
Right? And so then the question we want to ask is, which is the probability question, is what is the respective weightings for those 3 future paths of the observer, the ones in which they measure A, B, and C.
Yep.
We've already established, I think, that the completion steps will have path weights given by the product of the observer's path weight and the path weight of the thing they're observing.
I agree, but why are the completions relevant?
Right. So then it's the completions that lead to the branching of the observer, right? Because it's the completions between the observer and evolution A that lead to the path in which the observer thought A happened. The completions between the observer and path B that lead to the future in which the observer thinks
Okay, hold on.
B happened. Right?
I'm thinking about that. Thinking about how to really understand that. So we've got these threads of the observer, and
right. So the observer right now is just a single path. There are 3 possible paths corresponding to the 3 possible outcomes that they can see, A, B, and C.
Yep.
We apply completion steps between path A and the observer's path. That gives us certain completion steps. That defines the future of the observer. We could also
why does that define a future of the observer? That's saying that by talking about a completion step, you're saying the observer who thought they were going on one path might actually have gone on a different path because they coarse-grained together something which corresponds to a different path.
Right.
Okay, so a way to say this is the observer has a path they're going on, but by doing coarse graining / completion, you're fuzzing out the path that the observer might have taken.
Yep.
I see.
Right.
So the claim is that the chance the observer went down one of those other paths I see. The observer could have gone down.
The pathway to the 3 possible future paths of the observer corresponding to the 3 possible measurement outcomes is exactly the product of the path weights between the observer.
Can I explain why? Can I explain why? Because I think there's an easy way to understand this. The point is, the observer was on a train track, was on some track, right? The observer could divert from that track by any of those branchings and wind up on the other track. See what I'm saying?
Yeah.
But their chance to wind up on the other track, it could be any thread of the observer and any thread of the other track. Could be the thing. What's that?
Of course, yeah. That's why you get multiplicative.
I know. I'm simply trying to say this in the simplest possible way, right? So the observer is going down a train track, and the observer is a thread, is a collection of threads. A particular outcome is another collection of threads. Okay? As soon as any of those 2 threads connect, so to speak, that creates the possibility that the observer concludes that outcome. And the number of ways that can happen is the product of the number of threads in the two paths. But in addition, there's the question of the phase, which is basically the directions of those paths. And to get from one to the other, yeah, I don't quite understand. See what I'm asking? That the phase, how can I add that to this computation? So I've got these different threads, the threads of the observer, the threads of the process. They're all a bunch of paths. And what we're saying is, because you can think of it as a coarse graining, that any time any of those threads coincide, that would be the observer concluding that that outcome had occurred. Do you think that's correct?
Yeah.
Okay. So then what we're saying is, I mean, so I like this picture. So there's a bunch of threads of the observer, there's a bunch of threads of some process, and then anytime those 2 things coincide, this is nice. I mean, you probably think you've been saying this all along, but I'm slower. Anytime those things coincide, that's a way that the observer can think that that outcome happened.
Right.
Okay.
And so then the contributions to the future states of the observer in which they think each of the different measurement outcomes happened are exactly the products of the path weights for the observer and that measurement outcome.
Yes. Okay. Nice.
Which is the Born rule.
More or less. Okay. Let's talk about phase for a second. Okay. So I like this. This is good. But now let's talk about these two different. The picture is that coincidence of threads can only happen if you wound up in the same place in branchial space.
Mm-hmm.
And let's think. So how to think about that? How to think about, I mean, it's almost some kind of random phase approximation thing that is like, in order for you to get from this bundle here to a bundle at a different place in branchial space, you have to go through lots of stuff, which is your statement that you have to basically you have to complete everything you have to make every intermediate completion.
Right. Eventually your geodesics becomes so long that the multi-way system loses any structure.
Right. But so what we're saying then is that, okay, so there's two different ways to say this, I think. One thing, so the very fact that okay, here's a way to say it. The fact that the observer concludes that anything definite happened is a consequence of some level of coarse graining, because the system is going off in its paths in multi-way space. The observer is going in their paths in multi-way space. For them to conclude that they aligned with what happened in the system, there has to be some degree of coarse graining.
Mm-hmm.
But that coarse graining effectively has to operate in phase, so to speak, in the phasial direction, so to speak.
And so the greater the phase difference, the greater the information loss.
Right. Well, to put it a different way, right, the greater the coarse graining necessary to align those paths, which would otherwise be,
because what you're doing is you're collapsing down. You're defining some angle, and then you're collapsing down that whole angle.
Right. It's called the collapse of the wave packet.
Exactly. So the point is, if it's a pi by 2 angle, then you've destroyed the whole multi-way system.
Yeah, I understand. Okay, hold on. So, two effects. Path weights, because you are trying to see how many ways could the observer align with the observee. That's effect number one. Effect number two is, to align with the observee, you have to reach them in phase, so to speak.
Right.
And that could involve, see, the thing that's confusing to me is this. Just in terms of counting paths, to reach them in phase, it's just like there are gazillions of paths you need to follow. There are gazillions of choices for how you'd reach them in phase.
Mm-hmm.
But those paths, the fact that there are gazillions of paths, fuzzes things. I see. The point is, by the time you reach them in phase, you've reached everything else in phase as well.
Right. Yeah, exactly.
So the issue is,
the fact that there are so many geodesics is an indication that that their path is not uniquely defined. that there are many, many other possible trajectories that would also be consistent with those, with that geodesic cloud.
Exactly. But I mean, in the first case where you're multiplying path weights, it's like good that there are more paths, right? If the paths are aligned, it's good that there are more paths.
Right.
So you're getting more weighting by there being more paths. But as soon as the paths are not aligned,
then it's bad. Big magnitudes are good if they're constructive, but bad if they're destructive.
Well, I understand that, but what's happening is that all those paths are leading you to places
that aren't
don't align.
That aren't the place you want to go.
Right. So the question is, we should be able to see this explicitly. We should be able to make a toy model of this where we can see this. So got a bunch of paths. You are sort of injecting the observer. So you've got all these paths that are just doing their thing as the quantum evolution. You inject an observer into this whole thing. You're asking the question, or you're injecting this basis, path into the whole thing. You're asking the question, how many ways are there for that basis path to align with what you're seeing? Oh, I see. Well, I'm sort of seeing this. I'm not. I mean, I understand the basic intuition. I'm just not. I don't completely have this. Humph. We're really close here. This is basically correct. And by the way, this is considerably cleaner than we've had before, in case you didn't notice. I mean, maybe you already understood this, but I did not. At least not with this level of cleanliness.
I hadn't before made the connection that, and it's really obvious now that I think about it, that the linearity versus non-linearity of evolution and measurement is an additivity versus multiplicativity of state path weights. That's a really clean idea. And if correct, a very, very nice solution to the measurement problem.
In what sense?
Well, I mean, it explains why measurement can't be described by the Schrodinger equation, because the Schrodinger equation only adds path weights, whereas measurement multiplies them.
Let's ponder that statement.
Right. I mean, that's the core of the measurement problem, right? You're saying that the Schrodinger equation, which is the linear, that's the linear evolution equation, is the adding path weights as the multi-way system evolves.
No, I understand that.
And the measurement problem is to explain how you get something non-linear or apparently non-linear like measurement.
Okay, hold on. Let's think about this for a second. So, and the answer to that is, the reason it's nonlinear is you need to know how the observer's fiducial path plays onto this whole set of quantum paths that are going on.
Right.
You need to understand how the observer aligns themselves with that set of paths.
Yes. So it's as though you're taking a tensor product of the wave function of the observer and the system they're observing.
Which is an unsurprising claim.
Right.
But what's surprising is that the interpretation of the observer, let's walk through this one more time. So the interpretation, the question is, what did the observer think happened? And the way that we are describing that is we're saying, the observer thinks what happened is when something that happens in the system aligns with their expectations, so to speak, aligns with one of their expectations. And the way that can happen is by virtue of any of the threads in the observer agreeing with, ending up at the exact same place in multi-way space as any of the threads in the system. Being identical to a thread in the system, basically. That some aspect of the observer has become identical to some aspect of the system. And so the nonlinearity is because there isn't just one thread in the observer. Otherwise, there wouldn't be any nonlinearity, right? It's because the observer has multiple threads.
Right.
And the observer has multiple threads because they too are in the system.
Right.
Maybe it's like second-order cybernetics that I never understood.
I don't know this phrase.
Oh, I've tried to talk to people about this for like multiple hours, and I simply don't understand it. It's about a cybernetic system observing itself.
I see.
And it has weird pictures of eyes looking at themselves and so on. But I don't understand it, and maybe this is it. Okay, so let's go through this again. Yes. Okay, so the point is, if the observer is part of the system themselves, the observer is multi-threaded.
Yep.
And the claim is that
where multi-threaded could still mean single-pathed, just with weights.
Well, but I consider that multi-threaded because the fact that we're weighting paths is just a convenience for us doing math. The truth of the situation is there are multiple paths.
Yeah, I mean, Max has made this argument before. I don't think we fully understand the ontological significance of isomorphism yet, so to speak. I don't think it's immediately clear whether merging based on an isomorphism criterion is a fundamental part of the process or not. Given how important it is for causal invariance and things, I don't want to discount the possibility that it is important.
Well, I think that merging in our minds, merging is important because if it wasn't for merging, with respect to a mind,
anyway,
yeah, it sort of doesn't matter how you got there. And so with respect to a mind, it is merged.
Yes, right. That was my only point, that I think yeah.
Okay, so it is merged in the mind, and which we can represent as path weights. But in what sense? Okay, so it's an interesting question. You're right. I mean, if there are two universes and they're absolutely identical, or they're two, as soon as you put a mind on top of the thing, identical stuff is just the same.
Yep.
Okay, so I see. So then, in some sense, the role of the mind is to conflate identical things. And that, in other words, to turn what would otherwise be different threads into simply path weights. But either way, however we think about it, there's multiple threads, multiple path weights in the observer, but they have all been conflated by the observer because that's what minds do, is the claim. Minds attempt to conclude that definite things happen. That's what our way of, that's our way of understanding the universe, is to, coarse graining is a fundamental feature. Coarse graining either of identical things or of almost identical things is crucial to our attempt to understand the universe.
Mm-hmm.
But, so what's happening then is that the observer is that which is combining either identical or almost identical things. And the reason that there is something multiplicative going on is because the observer is multi-threaded and multifaceted in some way. So the observer So what does this have to do with all our discussions about coordinate singularities and QUAFs? What is a QUAF in this picture?
What do you mean by in this picture?
Well, in the picture where the observer, the basis states are these bundles of threads in the multi-way system.
Yeah.
Explain. I mean, QUAFs have more to do with comparing things. Well, okay, what?
I don't understand the question. I mean, the QUAF is how you define the simultaneity for that measurement operation.
Yes, I know, but that's a slightly different thing than this question here that we're now addressing of what's the relationship between simultaneity and the whole thing that we're discussing here? I think they're two orthogonal issues.
Are they? Why?
Well, we've got okay, the act of measurement. Okay, you're saying that we choose to you're saying we have to make a choice about when we do this, when we look at this correspondence between, okay, again, let's walk through this one more time. So the claim is the observer is this thread of this collection of threads. The Born rule, which I now know now what it is the result of that bundle of threads coinciding the projection of that bundle of threads onto a bundle of threads which might be identical to it. That was part of the actual evolution of the system.
Right. And which microstate in the observer's bundle of threads and which microstate in the system's bundle of threads are being projected onto one another is defined by the QUAF, is defined by the simultaneity surface, obviously.
Hold on.
That's the sense in which they're related.
Wait. I don't understand. Okay, so I see. So in other words, the observer is evolving through many microstates. The
Yep.
system is evolving through many microstates.
Right. And which one of which you project onto the other is determined by the QUAF. I mean, that's what.
Okay, what's the analog of that? Yeah, right. What's the analog of that in? Okay, is there any analog of this in relativity?
Yeah, I think so.
Okay, what's the observer in general relativity? In general relativity, the observer is a single thread. Right? This multi-threading is a consequence of the multi-ray system.
Sure.
That's a new feature, so to speak. So previously in the general relativity case, the only thing that was relevant was the simultaneity question for the observer. But now there's in addition the multi-threading question.
Mm-hmm. Right.
Okay.
But obviously the relativistic example is just saying that if you project one null ray onto another, it depends on your foliation choice. The result
Indeed.
depends on your foliation choice.
Right, indeed. Which in this case would be the same deal, that depending on your QUAF, you might get completely different results for the projection.
Of course. Yeah.
But that's a separate issue from the fact that there's a bundle being projected. So this is no longer the isolated geodesic has been eschewed, so to speak. There is no isolated geodesic anymore. In the case of quantum mechanics, the sole isolated geodesic can't exist because it will always branch. Whereas in general relativity, it's perfectly meaningful to consider a sole null ray.
Right.
But in quantum mechanics, there is no sole null ray. Can't happen.
Right.
The observer, and therefore.
But I mean, so the more direct analogy in the relativistic case would be you're computing projections of light cones onto one another, and you actually have to compute shortest distance between the horismus points on the two light cones.
Yes.
Which would also be multiplicative.
Walk me through that. So you're saying that, and remind me what the horismus point is.
The horismus is the boundary of the light cone. It's the surface.
Okay. Okay, so you're saying the common light cone will be multiplicative.
Right. If each ray in the light cone carries some unit of intensity,
then the joint intensity will be the product of the densities.
Right.
What about entanglement cones then? What is the joint entanglement cone? Is that meaningful? Is that a useful concept?
How is that different? Sorry, go on.
Well, the entanglement cone is a concept of all the sort of quantum spreading that can happen.
Right. I'm curious as to how you think the entanglement cone is different to what we've already been discussing.
Well, maybe it isn't.
The fact that the observer and the system they're observing are both threaded entities, as you say, is exactly the statement that there are non-trivial entanglement cones.
Well, maybe they are both entanglement cones. Maybe this threads is not really right. Maybe they're both cones.
Yeah, well, obviously in the unmerged case, they would be.
Okay. All right. That's a good way to think about it. So okay. So there's a bundle Yeah, but the point about it is most of them aren't going to the right place. Most of the things in those, look, in the entanglement cone of the observer, most of the rays in that entanglement cone are going to somewhere that isn't what you thought you were, that isn't your fiducial path.
Yep.
It's not a path you care about. On the other hand, that entanglement rate, that maximum entanglement rate, is a dilution rate for what you care about. And what is the meaning of that dilution rate? I mean, that's some kind of quantum decoherence thing. In other words, as time goes on, more of the possible outcomes are not what you care about. In other words, things are becoming more and more sort of quantum fuzzed out.
Mm-hmm.
Is that relevant to anything? I need my lunch. If you're up for it, I would be happy to go on in a few minutes and talk some more about rule space. I think we've made good progress on this quantum question.
Okay, I mean, is there a particular thing you want me to figure out with respect to rule space?
Not really. I mean, I think that the thing I'm trying to figure out, I'm trying to think, well, for example, the analog of all this stuff we're now talking about will be interesting to know.
Mm-hmm.
But I don't think there is a direct analog. I mean, so for example, one thing that will be nice to understand is right now the geodesics don't seem to have any particular significance in rule space. Well, they're the shortest non-deterministic algorithms. But so what?
I mean, what do you mean, so what?
Well, I don't know. I mean, the question is now, look, we've got a surface that represents the set of places that deterministic algorithms can go after t steps.
Yeah.
Right? We've also got a surface that is this place where non-deterministic algorithms can go after t steps.
Yep.
Okay.
Yep.
So what's that?
Yes. So we have representations of P and NP in effect.
More or less. Yeah, more or less.
Yeah.
And so the question then is, the fact that our representation of P is this big squiggly sea urchin, right?
Mm.
Is that a statement that P and NP are distinct? In other words, is the sea urchin, it isn't quite, okay, so take two different paths, take two different deterministic computation paths. There is a translation between them, right?
Yeah.
I need to get some food. We can. Are you up for continuing a bit, or do you want to?
I mean, I'd prefer it if there were a precise question that I could try to answer.
Well, I mean, yes. I don't know what the precise question is, because if I knew the question, I would probably be able to answer it. Roughly the issue is, given, we have this notion of translation in rule space, right?
Mm-hmm.
So we've got two deterministic. If you stop sharing, I can see my.
Oh yeah, sure. Sorry, I forgot I was still sharing.
Okay. So the question is, given two paths here, given two deterministic computation paths, this is what got us into the whole string figures discussion, right? Those two deterministic computation paths have a certain translation between them.
Yep.
It's a little unclear to me. Let me see. Right, they have a translation, but what does that translation, what the hell does it mean? I mean, every place where you have to go down a different branch of the non-deterministic system, what's the relationship between that and universal computation?
Sorry, but between what and universal computation?
The fact that you can always move from one path to another on the non-deterministic system.
But that is the claim that the system you're using is, well, it's the claim that the multi-way system you've designed is homogeneous in terms of its level in the arithmetical hierarchy.
Is it? I mean, I think that's something like that is right, but it feels too geometrical here.
Why? All you're doing is you're saying that your space is causally connected.
Yeah.
And if it weren't causally connected, that would be indicating that there were certain things that would be non-computable with respect to the other rules.
Okay.
Which would imply that you had at least two different levels of computation going on.
Well, you're saying the causal graph for this is always connected, you claim. Okay, the maximum translation rate. By the way, I mean, in that quantum case, the maximum entanglement rate tells us the reason that it isn't as important as it might be is that maximum entanglement rate is telling us, is telling us how quickly we can go to other parts of branch Hill space. I'm not quite understanding this. The issue is, what is the relationship between the maximum rate of measurement and the I see. Okay. Yeah, all right. So, but what's the relationship in, okay, for example, what is time dilation in Rullial space?
Slowdown. When you simulate one universal system with a different universal system, there's a slowdown due to the added overhead of the encoding.
Okay, so that's because basically, in order to get, so first point is, okay, so this is, okay, but, okay, look, just a second. So there's a question here of, causal invariance is equivalent to universality, is it not? That's saying you can always get
global confluence. Yeah. Is equivalent to universality.
What's the difference? I mean, universality, because you're talking about halting states and so on?
Right. I mean, yeah, obviously there are cases in which they're different, and I don't yet know how.
Well, that's probably has to do with all these transfinite crazinesses.
Right. Right.
Right. That's an interesting question, whether there is a notion of universality that applies even in the non-halting case.
Mm-hmm. Well, I mean, obviously it has to apply in the non-halting case.
I understand, but interpretation, it's a question of the interpretation of, look,
Yeah,
it's a question of the interpretation of translation for universality.
Yes, yeah, exactly.
In the non-halting case.
That's the problem, which is the same as the problem of interpretation of branch pair convergence in the non-terminating case.
Right. Okay, so causal invariance implies you can always get to a particular place.
Right. The reason I say homogeneity in terms of level in the arithmetical hierarchy as opposed to universality is that you could develop a multi-way system based on a non-universal computational system, but just where all of the rules have the same level of computational sophistication.
Okay,
and you still
let's talk about an example of that, okay? Is there
partial recursive functions?
Well, okay, hold on a second. So is there an example of a non-universal? See, the problem is Rulio MW system. Okay, so
I mean, if you want to get really technical, this Turing machine case is non-universal.
Why?
Because we have finite tape.
Yeah. Well, we don't have finite tape. This thing goes on to infinity. That's what I'm trying to do with this stupid limit of this group.
Okay, fine. As executed on your machine, it's
right.
Anyway, sorry. That was
but right. I mean, what bothers me about this is universality here looks absolutely trivial to prove. For this non-deterministic. Is universality of a non-deterministic Turing machine trivial? Seems like it's completely trivial to prove that.
Well, because it contains the deterministic universal Turing machine as a subset.
Well, I know that, but it is non-trivial to prove universality for a deterministic Turing machine, right? It's non-trivial to prove that there exists. See, okay, what does it mean that there's universality for a deterministic Turing machine? It means that there is a point you can start it at. There's a way of translating points you can start one machine at to points you can start another machine at by using another machine.
Yep.
There's a finite, ordinary universality. Is basically, you can translate starting points. By finite, there's a finite, you can translate starting points of one machine starting points and ending points of one machine to starting and ending points of another machine.
And intermediate points, in fairness.
Okay, fair enough.
You can translate any state of one machine to any state of another machine by using a third machine.
Well, but a finite, it can't be a non-halting Turing machine. You can, translate the trajectories of one machine to trajectories of another.
Yes, using a machine, as you say, that is strictly less computationally sophisticated.
Well, using with finite paths. Well, using a fixed machine, a fixed scheme, which always involves only finite paths.
Yep.
Okay, so this is saying we got two of these trajectories. we got a whole family of trajectories. I mean, in principle, I could draw for every one of these deterministic machines, right? I could draw where it goes from different initial conditions, right? It's starting at any point here, and any position here, and okay. So, given a machine, you can start it at any position in the multi-ray graph, right? Because those are all possible states. Is that true? Yeah, you can start at any point. At any point. You're allowed to program it to start at any point.
Yep.
Okay, so the family of trajectories made by one machine is convertible into the family of trajectories made by another machine. But actually, that's not quite true. A universal machine has the property that its family of trajectories can be converted. A non-universal machine does not. Basically, that its paths are somehow diverse enough that they can be converted to the paths of any other machine. Right? But there may be some machine that's so stupid that basically, for example, the machine that does nothing, right? It's just going to sit in one place. So the machine that just does, that all it does is freely stream outwards in this picture. Its head just goes boom off in some direction, right? That machine does not form enough of a basis in the space to be able to be by finite translation to be turned into another machine.
Yep.
Okay, but these deterministic machines, any given algorithm corresponds to a deterministic machine. So to ask the question about all possible algorithms with a certain number of steps is to ask the surface that you get to. Is it obvious? I'm sorry. Is it obvious that a non-deterministic Turing machine is universal? That it is obvious that this. Yeah, it's kind of trivially obvious that this extremely non-deterministic Turing machine is universal. It's less obvious. Okay, so we can have a slightly non-deterministic Turing machine might or might not be universal. Actually, that's an interesting question. What is the simplest? There's a lot of clicking, by the way. Are you hearing that clicking?
I'm hearing it a little bit. Yeah, hang on. Let me see if it's on my end. I'll mute for a second. You can tell me if it goes away.
There is no clicking anymore.
Okay.
What the click source? I suspect it's a loose connection.
My microphone jack seems to be incorrectly. I don't know.
Okay. Anyway, that's an interesting question. Is there a universal pair of two Turing machines? Right. So in other words, we know there's no universal Turing machine. That's an interesting question. I don't know the answer.
Right. It's an instance of the more general question of what is the trade-off between the intrinsic sort of computational power of the Turing machine rule and the power of the non-deterministic rule that picks which path to follow.
Right.
How do those things combine to yield the overall computational power of the NDTM?
Right. Okay,
that's something which we actually have a way of exploring.
Yeah, I mean, I think, okay, but here, as we fill this in with higher and higher levels of non-determinism, I mean, this is the ultimate extreme non-determinism, this picture.
Right, right.
And what's interesting is this picture is trivially universal.
Mm-hmm.
This extreme non-deterministic Turing machine is trivially a universal machine. Is that true? Am I missing something there?
Well, like I say, it's trivially homogeneous. It's trivially homogeneous in terms of its level in the arithmetical hierarchy. We cannot deduce anything about its level in the arithmetical hierarchy.
Okay, so let's understand what
I mean,
will be
we can in
lower
this
in the
particular case.
arithmetic hierarchy. What
We,
will
we
be
can
lower?
we can cheat in this case because we know it's an NDTM, and therefore, as I say, in particular, it will include universal Turing machines as a subset. But if you constructed something based on partially recursive functions, it would look exactly the same.
Well, what about finite state machines?
Or that, or whatever.
No, but it's trivially universal for a different reason. That is, you can get from anywhere to anywhere in it.
Given so it's homogeneous in the arithmetical hierarchy.
But I don't understand. I don't think the picture looks the same for a finite state machine. This picture clearly is not the same for a finite state machine. For example, it's finite for a finite state machine. My claim would be that anytime it's infinite, no, it's not totally obvious to me that you can get that this. I could imagine one of these that is.
But okay. As soon as it's infinite, then the question of causal invariance is not decidable. Well, so how is it? So in what sense is it trivially universal?
Well, it's trivially universal in this case because it's a very uniform structure, so it's very easy to see that it's causal invariant.
If you can. You only know that it's a uniform structure from running it a finite number of iterations.
All right, just a second. For what?
The only thing you can extrapolate from this, even if you prove causal invariance, is that it's uniform in its level in the arithmetical hierarchy. I don't see how that can be otherwise.
No, I think that's correct. But I'm trying to understand for what underlying rules do you get causal invariance? That's one question. Or i.e. get universality. So, for example, could we have one of these things that is a pure tree that just never, because this thing will always connect. This thing always connects. But I think, could we have an underlying rule? For example, let's imagine that we, e.g., neighbor-independent substitution systems. I bet those are, I bet the corresponding picture for neighbor-independent substitution systems.
Well, their causal graphs will be a tree, but their multi-way evolution graphs obviously won't be.
Yeah, that way it still will work. It's still the non-deterministic neighbor-independent substitution system will still look convergent like this, I think.
Yes, right. But as I say, obviously the definition of a neighbor-independent substitution system is that its causal graph is a tree.
Yes.
But not its multi-way evolution graph.
Well, anyway, it's obviously dinner time for you, and it's my lunch time. But I would be very happy to go on with this. But you sound like you want to.
I don't know. I don't entirely know what the question is. That's my.
Well, so I don't know what the question.
I'm having trouble getting my teeth into anything here.
Well, okay. I think one question would be. Okay, so I'm giving you a question here. The question is, what is the analog of Einstein's equations in real space?
Mm-hmm.
Okay, that's a question.
Yep.
What is the analog of simultaneity? What are some interesting reference frames in real space? Right, I think the interesting reference frames are, the P and NP. Yeah, it's computations that take a given time the different reference frames basically okay, a claim is different reference frames e.g. Okay, so an inertial frame, so a cosmological, e.g. cosmological rest frame just counting the number of operations, independent of what those operations are. So an inertial frame, I would claim, is a fixed weighting of operations, I claim. I wonder if that's right. I mean, you see the thing I'm saying? So I'm saying
Yeah.
as you look, I'm not sure that's quite right. Because the branchial space here.
Well, you're implying that the operations are laid out sort of horizontally, which I'm not sure is true.
Yeah, I'm not sure that's true either. I'm not sure that's right. I don't think it's correct.
What we really have to do is to construct a three-way tagged multi-space with space-like, branch-like, and rule-like separations. Then if you were only considering inertial frames with respect to the rule-like separations, then I think you're right. The problem is that you also have branch-like and space-like separations, which complicates it a bit.
Yeah. But the question is in terms of, so, I mean, like, for example, the question of the analog of Einstein's equations. So in this non-deterministic, so I mean, the difference here, okay, look, here's an important difference, is that parallelism, oh, this is interesting. The trade-off between non-determinism and parallelism, right? Okay, so here's the point. Look, parallelism in real space is actually parallel computing. We're so used to parallelism in these other spaces. In the other spaces, parallelism is taken for granted. Right? So for example, in a string substitution system, I mean, we could do a sequential substitution system. Right? In the case where we're doing a sequential substitution system, we would be taking a particular path in the multi-way system, in the string multi-way system. That's the direct analog. So the sequential, so oh, wait. So a particular evaluation strategy in other systems, a particular evaluation strategy corresponds to a is the analog of a DTM. And so I'm confused. See, each event, in the case of a string substitution system, you follow a path in the multi-way graph, and you're doing a bunch of different events, right? But those different events might be space-like separated things. They might be, or they might be, I don't know. What do you think the analog, okay, what is the analog of Einstein's equations in this case, in this rule space?
Well, the minimal set of geometrical constraints to ensure, preservation of the level of the arithmetical hierarchy.
Okay, the analog of energy in this case is activity in the system, that it actually did something, as opposed to just, well, no, that's not right either. My brain is shutting down. I need to eat.
All right.
Anyway, if you want to go on at all, or you want to.
We can do in a little bit if you want to.
Okay, fine. Let's.
All right.
Well, okay, see ya.
Talk to you soon. Bye.
All right, we were last seen somewhere in rulal space, and we were talking about. Let me just pull up what we were talking about here. By the way, apparently our glossary has a customer. Did you hear about this?
No.
I'm giving this talk to some group in Chile, I think in a couple of weeks, and they are having a sign language interpreter.
Ah, interesting. Okay, yeah, I see.
And they need a glossary because Danielle told them, I talk quickly, watch out, your sign language person is going to get very tired. So they have to work out what a multi-way system is in sign language first, because if they try to do that in real time, it'll be really hard. I think a multi-way system is rather easy. One can rather easily imagine what that might be in sign language.
I was going to say that we've basically invented a sign language notation just through gesture.
Right. Okay, let's go back to, let me pull up the picture of rulal space. So what we were talking about was the notion of translation in rulal space and what it means to kind of, what travel in rulal space is. Right, so one thing we're thinking about here is, and we're trying to work towards what are the Einstein equations of rulal space. What's even the significance of ordinary relativity in rulal space? I mean, it doesn't help that it's not obvious what kind of reference frames we care about. Just pull this up here. All right, there's our picture. So the first question is, what reference frames are interesting? What are the initial frames of rulal space? Did we lose you?
No.
You're on mute. Oh, no.
No, I'm here.
So one notion of the cosmological rest frame corresponds to operation counting. Do you agree?
Well, subject to the caveats that we already discussed. Yes.
Which caveat? That it depends what kind of operations you're doing.
No, that it depends on the type of separation.
What do you mean?
If it's the cosmological rest frame with respect to pure rulal separation, then I agree. If it's with respect to the combination of space-like, branch-like, and rulal separation, which is the canonical way we display these things, then I don't agree.
I see. Well, wait a minute. You're saying the successive layers of this geodesic ball, starting from a given point in radial space, correspond to operation counts, right?
What geodesic ball? It's a Lorentzian space.
Well, I'm saying you start from some point in the space, right? And you just grow this ball.
How can you grow a ball if it's Lorentzian?
You can just start from a point, and you do. I mean, you just follow each okay, ball cone.
Yeah.
I'm sorry, cone.
Okay. Yeah.
Okay. So. Okay. So wait a minute. So we have this notion of a well, analog of the light cone.
Right. Simulation cone.
Is it? I mean, it's a cone. So you're saying it's every state I can reach. Why do you call it a simulation cone?
Because it's intersecting with all of the geodesics that correspond to computations that can be simulated from a given state or from a given geodesic.
Remember, the computations aren't geodesics. The deterministic computations are not geodesics.
No, but the non-deterministic ones can be.
They are, yeah, sure. So it's the ones where, all right, so the crosshatch.
You have a path through radial space. You propagate a simulation cone. It allows you to work out which other paths through radial space could you reasonably simulate given a number of steps from a particular point on your present path.
Fair enough. That's certainly true. So a simulation cone says in T steps, what other computation paths can you simulate? Okay. And if you try to exceed the maximum simulation speed, if you try to travel in radial space faster than the maximum simulation speed,
yeah,
that means you can't get there by simulation.
Right.
If you sample states,
because your slowdown effect becomes infinite as you reach the maximum simulation rate.
Right, faster than rho t apart. You can't, well, what you can't do, you can't reach them in real time. Right? You could reach them by going on some circuitous path and coming back to them. Right? If they're less than rho t apart, then that means that in the time you've taken, in this t time you've taken, you could as well have gone to that state rather than the one you actually went to.
Right. Right. Each value of t puts an upper bound on the level of computational irreducibility of the things you're allowed to simulate.
Right. So, okay, so you can't reach them in real time, but so this is like saying, with respect to non-deterministic computation, this is like talking about equivalent computations, micro-equivalent computations, so to speak. Right, so the computations that are within a simulation cone are micro-equivalent in the sense, what's that?
Yeah, are micro-equivalent in the sense they can be simulated with slowdown no greater than t.
Yes, or they can be simulated in real time.
But what does real time mean? Real time, your definition of real time depends on your value of t.
No, I understand, but I'm saying that you could look. Time is a mess in these things anyway. But I'm saying you could go from the root, and you could follow this new computation rather than the old computation, and you can do it without slowdown. We're saying the same thing. It's
Sure.
a trivial statement, right?
Sure.
So that's characterizing for non-deterministic computations what you can reach. The issue is the simulation cone for deterministic computations might be something much messier. Right? The full simulation cone is for non-deterministic computation.
Mm-hmm.
Is there a deterministic DTM simulation? Well, it's not really a cone. Right? What is the analog of that? So that's asking, that's an evaluation front, I think. It's the analog in these other systems of an evaluation front. So I claim that the analog of an updating strategy is an event selection function. Basically, the DTM is a big event selection function. Do you agree?
Well, yes, it's a deterministic. I mean, by definition, it's a deterministic rule that picks events. But I'm not sure if that's a useful way of thinking about it. My analogy would be more something like the trajectory of a particle that's being acted on by non-gravitational forces.
Let's think about that. Let's talk about curvature in real space for a second, talking about gravity. What about commutators?
Yeah.
What is parallel transport? What's interesting about parallel transport? So you say you do one computation for a while along one GD-SIC.
It's obviously a measure of the non-mutativity of different, rule applications.
For sure. But what is the interpretation of that in computation theory?
Well, I mean, that is a concept in computation theory.
What is a concept?
Non-commutativity in term rewriting.
I know, but I'm talking about more traditional Turing machine stuff. I mean, what would be in computational complexity theory? Is there an analog of non-commutativity? So I'm trying to understand. I mean, I think non-commutativity is some statement about non-commutativity is a distributed computing statement of some kind.
How do you know?
Well, I'm saying that I think doing these operations rather than these operations in the different orders, like in term rewriting, is just a question of, is there microconfluence, so to speak? It's the same statement.
Well, okay. If your claim is that eventual consistency and confluence are ultimately the same thing, then I agree.
Right. No, but I think in terms of I'm not sure. Okay, but what kind of a question? Okay. See, I just don't understand GD6 in this rule space very well. And because I don't think that they have a direct analog. Again, what would Okay, so first of all, what would relativity, what's the analog of special relativity? Special relativity gets interesting when you can talk about inertial frames.
Yeah. I mean, special relativity is computational irreducibility.
You claim basically special relativity is the constancy of the speed of simulation.
Yeah. And it's saying as you attempt to reach the speed of simulation, you get time dilation, which is slow down, and you get length contraction, which is the analog of kind of space complexity bloat.
Let's think about that claim. Okay, so constancy of speed of simulation. Okay, so as you approach speed of simulation, you get time dilation. I guess that's true. Okay, what do you claim that the analog of space Lorentz contraction is?
Lorentz contraction is increase of space complexity, isn't it? Oh no, a decrease. It's the trading off of space complexity for time complexity. That's what I mean. That's what a Lorentz boost is.
I know Lorentz. Okay, so what is space complexity in this context?
Rulal extent.
Is it? I mean, because it's not. It's something. Yeah, it's something about distance in Rulal space.
Yeah, it's extent along a rule-like hypersurface, but not a pure rule-like hypersurface. A combination of space-like, branch-like, and rule-like separated.
Okay, so the claim is that a boost is a mixing of space and time complexity, so to speak. Space and time costs.
Right. I mean, because think about it. If there are essentially how can you increase your space complexity? Well, you can have just like larger states, which is increasing space-like separation. You could have more space-like states, which would be increasing branch-like separation, and so on. And so all of these things are conduits to separations on a rule-like hypersurface.
Just 1 second here, sorry. Sorry, say that again. Sorry, I got distracted.
So obviously, there are multiple ways you can increase space complexity. You can increase the raw size of the state, which is increasing space-like separation, or you can increase the number of states in some superposition, which would be increasing branch-like separation, and so on. And so these are all conduits to the separation distance along a rule-like hypersurface.
Yes. Well, I mean, basically, rulal distance measures essentially difference in degrees of freedom, difference in...
But it's a measure of the Fisher information distance between two states.
Remind me what the Fisher distance is.
It's an algorithmic information complexity measure. So it's telling you the size of the shortest algorithm necessary to convert between one state to another state.
Right. Well, but I mean, it measures basically something about hold on 1 second. Sorry. Okay, but all right. So your claim is that when I do a boost, what am I doing when I do a boost? I'm saying I'm a little confused about how I can actually use the trade-off between space complexity. So actually, well, the other trade-off will be between non-determinism and time, right? I mean, the trade-offs. Look, trade-offs. The trade-off possibilities are space, non-determinism. What is the case of branch Hill? What's the branch Hill one?
Well, it's the distance between superposition states.
No, I understand that, but that is that non-determinism, or is that's what is that one? That's parallelism. That's parallelism.
Right.
So in other words, that's space-like. Parallelism is branch-like, and non-determinism is rule.
Right.
Okay, and then there's time. So you can use more space, you can do things in parallel, or you can use non-determinism and use different rules.
Mm-hmm.
Okay. And the fact that walk me through. Okay, so constancy of rho is saying that I'm still a little confused about how you use that to make something like special relativity. I mean, in other words, you're saying as you move in those things, I see.
Yeah, reducing space complexity, parallelism, or non-determinism necessarily incurs an increase in time complexity and vice versa in order to maintain consistency with, the geometrical implications of rho.
Let's just walk that through for a second. So you're saying in order to, normally you're going sort of straight down in the multi-way graph. If you were just doing sort of the shortest path.
Uh-huh.
But now, so is there a quantitative way of getting this? In other words, is there a quantitative trade-off between these things? Because that's not something you usually have.
Right. But yes, I mean, to the extent that we can define a metric on the space, yes, we can define a Lorentz transform.
But so for the case of Turing machines, is it a Lorentz transform? I mean, is it? So we know what the metric on the space is, more or less. I mean, we don't actually know yet, but we will know. So how does the Lorentz transformation relate to? If the space is locally modeled as Euclidean, then we have the standard Lorentz transformation, or locally modeled as Minkowskian.
Mm-hmm.
If it's exponential Minkowskian, what do we have for the Lorentz transformation? Is it still the same?
Well, there's the generalization of it that I defined for the multi-way Minkowski norm.
What thing? What is that?
I mean, basically has the same form as the Lorentz transformation, just with 2 additional degrees of freedom, or 2 additional terms that come into it from metric.
What do you mean 2 additional terms? I mean, so normally there's a, 1 over square root of 1 minus beta squared.
Yes, I know.
But so what are the additional terms?
Well, one is the an I times square root 1 minus beta squared that comes from the positive imaginary eigenvalue of the multi-way Minkowski metric. And then the other is a minus 1 plus I time contribution.
Well, so bottom line here, what is, if we're trading off space, parallelism, non-determinism, right? We're trading those off. What's the formula? What is the formula for gamma?
Well, I haven't worked out the Lorentz transformation for this generalized metric yet. I mean, I can do, but
I think it'll be interesting. Well, because what would it give us? It would give us, given a measure of parallelism. Okay, so with respect to the space as illustrated on the left, we should have a definite parameter that represents each of these things: the amount of non-determinism, the amount of parallelism, the amount of space being used, right? The length of the tape, the number of, the number of parallel branches, they all have actual measures of stuff. So now we should be able to get a relativistic transformation that says, okay, so one of the confusing things is when you increase the time, normally as you increase the time, you go a certain distance in something like space, for example, here. So what this is saying is, as you increase the time, you're using more parallelism.
Yep.
So then what we expect is that there will actually be a completely quantitative trade-off. What's that?
Yeah, what it would do is it would give us a precise quantitative bound on the degree to which P space, NP, and NC are related.
Indeed so. Indeed so. And we're utterly spoiled because people have been looking for that for years. So in fact, the way it would work in this Turing machine case, we should be able to do it quite explicitly because we can actually compute the parallelism, we can compute the spatial, we can compute the radial distance associated with each of those quantities.
Right.
And then what should happen is we should see, we should have a combined formula You know what's odd here? I mean, I don't know, maybe because of polynomial time and so on, things like square roots would never have been seen. Because I mean, usually in p space versus p, and there's usually an exponential difference between these things.
Mm-hmm.
But in our setup here, we'll something like the spatial degree of freedom is going to be a k to the n. There's going to be the n is going to be the distance in real space, and the k to the n is going to be the actual counting.
Right.
All right, so if that's special relativity, what's general relativity? What's gravity?
Well, I don't really have anything to add to what we already talked about.
Remind me what you claimed.
The general relativity, in the same way as general relativity is the most general set of constraints needed to ensure asymptotic preservation of dimension in the causal network, it's the minimal set of constraints required to ensure asymptotic preservation of the level in the arithmetic hierarchy in Rullial space.
Let's be more specific. So we got a bundle of GD6 in Rullial space.
Yeah.
The statement of relativity would be something about the fact
gravity is the thing that prevents them from diverging, i.e. prevents them from going off and performing computations of different inequivalent levels of sophistication.
Explain. So I mean, but we're saying that
if they don't converge, right, if they diverge, then that means there isn't a geodesic path from at least one of those geodesics that maps onto the other.
Yes. Okay, I understand. So
which means they're inequivalent.
A bundle of GD6.
So gravitation is the force that prevents that from occurring. And so general relativity is the most general set of constraints you need to preserve level in the arithmetic hierarchy.
Okay, a bundle of GD6 can't diverge without bound. Otherwise, you wouldn't be able to cross-simulate them.
Right. Just like if they diverged without bound in a causal graph, you'd get something that didn't have fixed dimension.
Okay. But what is that interpretation? What's the interpretation of that as? Oh gosh, what's the interpretation of well, okay, so what's the analog of a black hole then?
A region of computational reducibility. Right, a black hole is a region in which the level in the arithmetic hierarchy is strictly lower than in the surrounding region. Because the outside can simulate the inside, but not the other way around.
Region in which GD6 allows simulation, enter but don't leave.
Right. Partial recursive functions would be a black hole in the space of general recursive functions.
Yes.
For instance.
Total recursive functions. Yeah, total recursive functions.
Yeah.
Primitive recursive functions. That's what we meant. Both.
Oh, primitive. Sorry, why did I call them partial? Sorry, yeah, I'm tired.
We both meant to say primitive.
Primitive recursive functions. You're right.
Right. Which, i.e., computationally reducible. Okay, what about a cosmological event horizon?
Well, those are just somehow totally incommensurate models of computation. It's not that one is strictly stronger than the other.
But we don't have examples of that right now.
No. And there's... Yeah. So actually, that's a nice way of thinking about it, right? So a cosmological event horizon is the situation where the encoding between two different computations is itself is an undecidable problem.
I see. Encoding is undecided, but encoding to convert.
Right. Because it would require an infinite number of steps to move from one GD6 to another.
What's an example of that?
I mean, bear in mind, it only has to be undecidable with respect to the model of computation of the actual space. So if you had, if we take the primitive recursive case, if you had the space of primitive recursive functions, but you had two primitive, I don't even know, this is probably an elementary thing about mathematical logic that I don't know the answer to, but could it be the case that you had two primitive recursive functions, but where encoding the problem of mapping one to the other requires a general recursive function.
Yes.
Can that happen?
Yes.
Okay. Then
worse.
that's a cosmological event horizon.
Worse, it can be undecidable whether the two primitive recursive functions are equal on things.
Right. Okay. Perfect. Well, that's a cosmological event horizon, I think.
But only for things that are below the standard level of universal computation.
Yeah. But I mean, universal computation is great and everything, and it gives us physics. But there's nothing to prevent us from constructing Rullial spaces for oracles.
Sure.
I'm trying not to privilege Turing universality too much in this discussion.
Fair enough. Okay. So the analog of the Einstein equations we claim here. So we haven't talked about energy very much here. What is the analog of the non-vacuum Einstein equations?
Well, we don't even really understand that for the branch yield case. I have no idea.
Let's think about that actually for the branch yield case. So there's probably a generalization. So that is quantum gravity, basically.
Right. Yeah, I mean the problem. I mean, yeah, what we really have to see is we have to find some particles and then see what are the topological structures they produce in space-time causal graphs and how do they compare to the topological structures they produce in multi-way causal graphs. And that, yeah, as you say, that's really the quantum gravity story.
Well, this point about what is the analog of the Einstein equations in the multi-way graph, I mean, part of that story, I mean, we believe part of the story is the path integral. But that's
a vacuum case, or at least it can be formulated in a vacuum way.
No, it can't. It needs a Lagrangian. It just doesn't have a spatial component.
Yeah, but so too does the. I don't understand the vacuum Einstein-Hilbert action in our formulation requires energy. It requires the causal edges to maintain the background space.
Sure, but
the point is that in our general relativity derivation, what we do is we explicitly break the equivalence principle, post hoc, because what we do is we say, because the standard formalism of GR separates the energy momentum tensor from the cosmological constant term, we do the same thing. We separate off the topological obstructions from the background space, but fundamentally it's all just energy. The same thing is happening in the branch yield graph, right? There's some kind of topological obstruction thing going on in the multi-way system, but we don't yet, I think, have a good classification of what that is. So my argument is that we can do exactly the same thing. We can split off the cosmological constant term, which is the thing that's actually maintaining the multi-way system and causing it to grow, and the localized topological obstruction stuff that we don't really understand.
Yes.
And presumably the same thing is going on in Rullial space, but that will presumably be even more obscure as to what a local topological obstruction would look like. But I think the cosmological constant term we can probably understand in Rullial space.
And what is it? I mean, it's maintaining all that activity. So another thing, okay, like modeling us as observers in Rullial space. What do our ROFs look like? Are they very rough, as one might think from their name? In other words, one description what does it look like if we say this is the rule for the universe? What is that looking like? Is that one of these things that's like a coordinate singularity in Rullial space?
Yes. Yes. I mean, all theories are coordinate singularities in real space at some level.
Okay, so the claim is a specific theory has to follow a particular non-geodesic path in real space. Okay, why is it a coordinate singularity? Because we are trying to prevent divergence. We're trying to prevent Rullial divergence.
We're trying to construct a region of computational reducibility where one does not exist, naturally.
Okay, well, we need to, wait a minute, we need to prevent Rullial divergence, basically. But in what sense? Okay, as we go down one of these weird paths that corresponds to a deterministic model, what we're doing is we're trying to, okay, we're trying to prevent all time evolution except the one on the path of our particular DTM. Right, that's our goal.
Yep.
Now, how do we see evidence? So we have quantum mechanics, which shows us evidence. We have quantum mechanics with H bar that shows us evidence of the fact that we can't ultimately do this, that there is entanglement divergence, right? What is the evidence of Rullial divergence?
I mean, is it not just the diversity of the computational universe?
No, but quantum mechanics is something we can measure. Quantum mechanics, so I'm saying you can do a measurement and you can say, okay, listen, here's where it really gets funky, right? Think of the observer in Rullial space.
Yeah.
The observer, as in branchial space, must be a bundle of threads.
Yeah.
So what's the analog? What I'm looking for is, what is a quantum effect in Rullial space?
Right. I mean, it's like any other coarse graining effect, isn't it?
To wit, what?
Well, I mean, just as coarse graining in space-like directions gives you statistical mechanics, coarse graining in branch-like directions gives you quantum mechanics. Coarse graining in the Rullial direction gives you kind of subtle ambiguities about which rule is correct given data that arises from the fact that the observer is computationally bounded.
Well, so your claim would be, it's the analog
Because
quantum
I'm a
mechanics.
computationally bounded agent, if I look at some phenomenon
Right.
and I ask,
Failure of inductive inference.
Right, exactly. That's a good way of thinking about it. Yeah. That there will in general be an equivalence class of rules that are consistent with my observations, and that equivalence class is my ROF.
Yes. But in particular, let's just walk through this for a second. The analog of quantum mechanics. Quantum mechanics is the statement that you don't know which path it took in branchial space. This is the statement. You don't know which path it took in Rullial space, aka you don't know what the actual underlying rule is.
Right. I mean, it's the ultimate generalization of your MKS thermodynamics story, but it's the algorithmic complexity variant of that. In the same way as a complex system will encrypt details of its initial condition, it will also successively encrypt details of its own algorithm.
Yeah. Fair enough. That's a good way to think about it. Right. So it's saying that analog of thermodynamics, Rullial evolution encrypts. Well, it's not quite the same thing, is it? I mean, what algorithm is being used, but that's not quite the same thing, I think.
Why not? Because if you're trying to determine which algorithm is being used, you're trying to determine which path through Rullial space led you to this point.
Yes.
But the argument is that there will, in general, be many, given the data that you're actually able to observe, there will be many different paths that are consistent with that data.
Okay, so your point is, analogy to thermodynamics, given a coarse-grained observation of the universe, there will be many paths in Rullial space that will achieve them.
Right.
That are consistent.
So, as I say, classical thermodynamics is saying that there'll be many initial conditions that are consistent, but the Rullial thermodynamics is saying there'll be many algorithms that are consistent.
Yeah, okay. Okay, what's the Rullian analog of heat?
That's a cool question. I can tell you're trying to zero in on the energy in Rullial space problem.
Among other things, yes. What's the analog of what's the branchial analog of heat? I think it's just the fact. Look, I think in all these things, it's basically just random activity.
Yeah.
And it raises the question: what's the branchial analog of temperature?
Yeah, hang on. Isn't the Rullian analog of heat non-determinism, degree of non-determinism, or at least related to it?
Well, they're all related because non-determinism in Rullial space is related to energy in Rullial space.
Right. Right.
As it is, by the way, in branchial space. I mean, non-determinism.
But non-determinism in a different sense, yeah.
Why is it different, actually? I mean, it's different because it's
non-determinism at the level of the rule as opposed to the level of the place where the rule gets applied.
Yeah.
One of them is, this is ultimately the difference between non-determinism in quantum mechanics and non-determinism in theoretical computer science.
Sure. Okay, so then, so non-determinism in Rullial space is related to some kind of energy. So remember our psi parameter, that is the number of threads in branchial space.
Uh-huh.
This is very wild, but here's what we need to know. How many threads are there in Rullial space?
Right.
Okay, so this is our units question. Units in Rullial space. What is the value of rho? Okay, so how do we compute that? So we need to know, let's say we knew, if we knew the number of parallel threads in real space, then we'd have some idea. So let's estimate the number of parallel threads. So I claim the number of parallel threads is the number of rules. So let's say there are n degrees of freedom in the universe. So how many degrees of freedom do we think there are in the universe? There's psi degrees of freedom in the universe, are there not?
Oh, yeah, on the order of.
Let's try to remember what the actual setup is. Okay, so we have the number of nodes in a slice of the multi-way system is psi.
Mm-hmm.
Okay, but so what are the number of possible rules? The number of possible rules. Okay, so number of possible rules is how big can a rule be? A rule, the LHS of a rule, is at most the size of the universe, right? Which is otherwise known. Now, assuming there are no branchial rules, assuming there are only spatial rules, which may not be correct, but let's assume there are only spatial rules, that's equal to the elements in the spatial hypergraph. Ten to the 184 times psi. Okay, so 10 to the 350. So I claim that the answer to the number of possible rules, let's see, if the number of nodes in the hypergraph is 10 to the 358 nodes in the hypergraph, how many possible rules are there? If you have n nodes, the number of possible rules is given by, we look at the section called the number of possible rules. Okay, it increases with its Bell numbers. Faster than exponentially. Let's see, K. That's okay. N is the number of relations. So the number of relations. Okay, so it's on the order of number of rules is of order 2 to the 10 to the 358. It's not a particularly small number. Okay, so that's the order of magnitude of the number of possible rules, which I believe gives us the number of parallel threads, if I'm not mistaken.
Right.
So given the number of parallel threads.
Except that we don't know the degree of, I mean, just like in the branchial case, we don't know the degree of degeneracy, right? We don't know how many of those rules will yield isomorphic spaces.
Yeah, right, that's right. Okay, but given that, we should be able to estimate. So given that, how do we estimate rho? That's what I'm asking. So I mean, here we had H bar to guide us.
Uh-huh.
But we don't know, what do we have to guide us with rho?
I'm quite taken with the idea that, in much the same way as the ratios to time in the spatial hypergraph give C, and the branchial graphs give H bar. I'm taken with the idea that there's some immediate interpretation of Chaitin constants in terms of separation distances in Rulliol
Yes,
space.
but I don't see that because Greg's number is something different. I mean, it's the
it's singularity density. I know.
right, but what should it be? What is the thing that gives us the scale here? So this is asking up to that degeneracy. Dang, what is the thing that gives one?
Well, it's it's the expressive power of Turing machines. However that gets quantified.
Look, the constant is, yes, you're right. The constant is I think we can do it relative to the universe. I think we can measure this. Okay, so what we need is the measure of it's something about the program length. How does it work? Okay, so my claim is we can actually measure this relative to the universe. And that what this is going to be is it's going to be, in the end, something going to be linked to the number of elementary operations, Something like this, something like that. No, why is it? It's not exactly that. Or maybe it's conversion between program length and actualization in the universe. Maybe. Come on, what gives us this? This, we should be able to figure this out. What are the relevant parameters in algorithmic information theory?
Relevant to what?
Anything. I mean, there's, for example, there's the question of program length complexity. So, for example, e.g., in AIT, there are questions like busy beaver, busy beaver of T, or busy beaver of program length. Right? That's an example of a parameter. How much for a program of a given length, how much activity can it generate?
Right. Which is of course the upper bound on branchiness.
Well, it's related to it, not quite busy beaver because the busy beaver is a finite case,
Hmm.
right? The busy beaver, it's going to halt eventually.
Right.
But what's interesting is the busy beaver is a non-commutably large thing as a function of program length.
Mm-hmm.
There's sort of the question of the busy beaver universe. Busy beavers in our universe are things that last as long as they could before hitting a space-like singularity.
Right.
Right, so the survival of our universe.
Oh, cool. Hang on. I found a thing. So there are infinite time busy beaver generalizations, but you're going to love this. Their behavior depends upon which infinite number of steps you pick.
Oh, cardinality of infinity.
So actually, omega and omega plus one infinities act differently with respect to the infinite time busy beaver, apparently.
That is interesting. Okay, well, hold on a second. The one question is the survival of our universe. Maximum time before space-like singularity. Because eventually, most things, it is claimed, are going to wind up inside a black hole, i.e. at a space-like singularity.
Well, that was why I brought up Chaitin's constants.
Explain.
Well, so Chaitin's constant is a measure of the density of singularities in rule space, right?
I don't get that. So you mean omega?
Yeah.
So that's the probability of halting of a universal Turing machine.
Yeah.
Explain why that's the... Oh, I see what you're saying. I see.
So a halting Turing machine is a singularity in rule space. So Chaitin's constant gives you the density of those singularities overall over infinite time in rule space.
Oh, that's very interesting.
And so in exactly the same way as if you know C and you know lambda in the universe, you can estimate the density of black holes. In the same way, if you know the rule lambda and the rule C, you can estimate Chaitin's constant.
Okay, let's understand this, okay? This is the density of black holes in rule space, basically.
Right.
Oh, that's really interesting. That is really interesting.
Mm-hmm. I wouldn't have brought it up otherwise.
Okay, so what you're claiming is, what do you mean you can estimate the number of black holes from C and lambda? How do you do that?
So obviously if you know the expansion rate and you know and then you know the energy density that you need in order to obtain in order to reach a Schwarzschild radius, which is what C gives you, then you can estimate, subject to certain homogeneity conditions and things, you can estimate the sort of a universe's propensity for producing black holes. And so you can produce there are models. I mean, Smolin has one that I don't particularly believe, but there are more believable ones where you can estimate over infinite time a particular universe's propensity for producing black holes.
Okay, so in space-time, you're claiming, given...
And as I recall, I may be misremembering the argument, but I think it ends up just coming out as a function of C and lambda, I think. Oh, and G.
Yeah, obviously G is involved.
Yeah.
C and Schwarzschild radius, basically. C.
Lambda and Schwarzschild radius.
Yeah, C, comma G, and lambda. Can one estimate what it is claimed? One can estimate the density of black holes.
Right, or at least so. Basically, people use this in cosmology to estimate, over infinite time, what proportion of the universe ends up in black holes and what proportion ends up in.
What's the answer? I would have thought it was either 1 or 0.
So if you neglect Hawking radiation, it's actually neither. It's somewhere in between, because you basically get some stray and sorry, neglecting Hawking radiation and assuming the value of lambda that's currently observed, you would end up with some proportion of the universe just in stray photons, some proportion of the universe in black holes, but the expansion rate eventually becomes sufficiently high that those photons never interact with the black holes. Obviously, if you include Hawking radiation effects, then the black holes eventually.
What's the analog of lambda in Rule space? The expansion of the universe in Rule space.
That's kind of inequivalent non-determinism, somehow.
Right. Well, what is the expansion rate of the universe? Oh boy, we haven't even thought about this in Branchial space. What's the expansion rate of the universe in Branchial space?
Well, that's a quantum information theory kind of story, right?
It is, yeah, for sure. But what is it? I mean, what does it represent? Is the universe expanding in Branchial space? Answer: surely yes.
Right.
But it isn't expanding right around here because why? Or is it? What are the galaxies of Branchial space?
Yeah, I don't know. I mean, yeah, as I say, I'm not even sure we know what the topological obstructions of Rule space will look like. Oh, sorry, Branchial space or Rule space.
Right. Well, okay, so there's what are particles in Branchial space, which is basically quantum gravity, I claim. Is the universe expanding in Branchial space? What the hell does that question mean? That means is the number of degrees of freedom increasing over time in Branchial space? If it is,
yeah, it's the question of do quantum computers work?
Why is that question?
It's the expansion of the universe in Branchial space that allows you to get exponential speed up, isn't it?
Maybe. Okay, so what's the redshift in Branchial space? Okay, I bet, okay, so insofar as it is expanding, one could get exponential quantum computing speedups. Oh, wouldn't that be interesting? If that speed up is like the expansion of the universe, like we don't get to use technologically anything about the expansion of the universe. Right? It's not like we can have, donkeys don't have to pull as hard because of the expansion of the universe.
Right. And the argument is the same in both cases, in exactly the same way as you say our measurement procedure increases in complexity as the branch-like hypersurface increases in size. We also say, our technological apparatus expands as the universe expands, so we can't exploit it to do useful work.
Right. That would be interesting. If the answer is quantum computers work only insofar as Branchial space is expanding, then everybody wins.
That has to be true, doesn't it?
What's that?
I think it does have to be true.
Yeah, I think it has to be true. That insofar as Branchial space does not expand, you can't get anywhere with a quantum computer ultimately.
Right. And so measurement, so maybe the answer to your question is measurement apparatus is the analog of a galaxy.
Yes.
In the sense that it sort of defies the global expansion of Branchial space.
I think that's right. I think it's a thing of fixed, which is measuring a fixed set of quantum degrees of freedom and not subject to the overall. So what is subject? How far away do you have to get before In other words, when you have these things on the opposite sides of the Earth or whatever that are sending, random, photons that or might not be sending photons to each other, is that big enough that you're subject to the expansion of branch Hill space? In other words,
but branch Hill space is expanding in the branch-like direction, not in the space-like direction.
oh, I'm aware. I'm aware.
The fact that they're on opposite sides of the Earth.
It doesn't matter, but I'm just saying that they just don't have connected quantum degrees of freedom.
Right. But if he is,
I think the issue is, are they quantum coherent?
I was going to say, yeah, exactly. Anything that doesn't have coherence will be subject to
anything not quantum coherent will be subject to the overall expansion flow. How can we be this far into the project and not have thought about expansion of the universe in branch Hill space?
It's the embarrassment of low-hanging fruit riches.
I know. Well, and the Big Bang in branch Hill space is just the beginning of many quantum degrees of freedom. It's nothing very exciting.
Right.
Inflation in branch Hill space happens all the time. Nothing special, because branch Hill space is exponential dimensional, probably.
Yes, although the idea that you could have, that you might get effective deviations for, so yes, branch-like hypersurfaces increase exponentially in size generically, but the idea that there might have been a phase transition where it didn't increase exponentially for a bit, or sort of started off being very well connected and then converged down, that's something we haven't really explored in the branch Hill case.
Right. Could there be cosmological All right, so given that, the expansion of the universe in Rule space, the analog of a galaxy in Rule space is something where you have a hope of being able to coherently explain it.
Right. It's a deterministic interpreter.
Okay, so
something that's unaffected by the non-determinism of the rest of Rule space.
Right. Right. A description language a description of the universe that remains coherent, I think, and is not shredded by non-determinism.
Yes. Assuming your definition of description requires that it be deterministic.
Okay, but so now, okay, the maintenance of space. Wait a minute. Okay. By the way, that's actually something relevant to space-time. Has nothing to do with real space. Back to black holes in real space. So black holes, these places where you cannot reach they are rules that didn't make it, so to speak. I mean, Chaitin's omega is really initial conditions, but that's okay. It's interconvertible.
Right. Why do you mean it's initial conditions?
The omega quantity is the probability that a single universal Turing machine does not halt, given different initial conditions.
Really?
Yeah, it's the usual definition. And it was Greg's original definition.
Okay.
I mean, it could be the density of it'll be equivalent to generalized. I mean, generalized omega would be.
Well, yeah, I get, but as long as the Turing machine is universal, then as you say, that's trivially interconvertible with saying that a particular Turing, that a randomly chosen Turing machine for some encoding will halt.
Right. So the answer to this quantity, approximating it by elementary cellular automata, the answer to omega is probably about 0.7.
Okay.
Right. I mean, about 0.7, 0.8 of the universal cellular automata aren't universal. Now, as we were talking about earlier, PCE implies that this density is just going to go up and up. And eventually, pretty much everything will have enough degrees of freedom that it can be universal. And probably with non-determinism, that happens much more quickly.
Right. Right. Just like how you can assemble a generational multi-way system state by imposing equivalence classes between branch-like separated states, but you could also just wait for that generational multi-way state to occur, naturally.
Yes. What's that like?
That's the same statement as that you can speed up the process of achieving an effectively deterministic evolution by doing a non-deterministic evolution and then defining a ROF.
Okay, so this is the analog between NDTM versus DTM is like generational states. Well, it's like.
Well, yeah, it's like
versus just waiting. What's that?
Right. It's assembling generational states versus waiting for generational states.
Right. So with an NDTM, no, with a DTM, you are explicitly assembling generational states.
No, wait. Okay, I was going somewhere different, but maybe this is right.
Well, I'm not sure. I mean,
because the NDTM is the thing that
NDTM it will eventually find that state. find the state you want. But you may have to go through many non-deterministic paths. Not sure this is quite right.
Yeah, no, I think it's actually, I think it's the other way around, right? It's
Yeah.
if you can run an NDTM in parallel, then you can assemble a generational state before the associated DTM would have reached it.
That is the right way around, yes. With an NDTM, you will get fragments quickly that you can assemble into a state that a DTM will eventually reach. That's the correct statement, I agree. Okay. Let's go back to estimating rho for a second, see if we have any hope. There's a density of black holes. What the hell is rho? What is it? How does it connect? Okay. It's the rate at which one can.
But you see my point about that. I mean, like the higher rho is, the smaller omega should be, I think.
Well, you're saying, okay, the claim would be
right, because
higher. Yeah, it's harder to make a black hole. Higher
exactly.
rho is the harder it is to make a black hole. Analog of the larger C is the harder it is to make a black hole.
Right.
Okay.
I just don't know the way you quantify. Well, I guess nobody knows the way you quantify the relative speed up of non-determinism versus determinism, because if they could, they would have solved P versus NP. But I'm thinking.
Wait a minute. Why is this that? Why is this that? This is.
No, this is the other thing, right? My point about Chaitin's constant was that there are two things that you need to know. You need to know Chaitin's constant. If you want to determine rho, you can work it out, I think, by knowing Chaitin's constant and by knowing the effective expansion rate.
Well, Chaitin's constant is of order 1. So whatever you want to do, just
right. It's shockingly big, or at least I always think it's bigger than I think it should be.
Okay, so it's of order 1. So that means given C and G, otherwise known as rho. So what's the analog of lambda?
Well, this is what I'm trying to work out, right? So my thought is that it's the analog, because basically what it's measuring is the relative speed up of doing non-deterministic versus deterministic evolution.
Why?
Because it's the amount that you're able to tree out in rule space compared to just following a single path.
Why is that lambda?
Because the amount of treeing out you do is the amount of expansion, isn't it? If you construct a rule-like hypersurface,
yeah, right. No,
the rule-like hypersurface is bigger.
Okay, but lambda is not. I see. Lambda is the exponential constant in the expansion. So
right.
So
what we need to know, I think, in order to work out rho, for at least in this way that I'm suggesting, is to know what the relative speed up of an NDTM over a DTM is, if you do this assembling procedure. But I think that's I think that's probably an open problem.
Well, hold on. So lambda is the base of the exponential what is the actual formula for the expansion of the physical universe? What units does lambda have? It has some G's that it's something. What is the actual formula? I mean, the formula for the expansion. What's that?
Right. Yeah. I mean, yes, it has
basically lambda to the t.
Right.
Lambda to the t with various c's, and I don't know what is the exponent there. It must have dimensions of time, of inverse time rather.
Right.
Okay.
Yeah. I mean, okay. Yeah. The Hubble constant squared is approximately lambda in the large scale limits.
Okay. That's odd. That's not suggesting exponential expansion. That's a non-trivial fact. That's not just a fact about exponentials.
Right.
Okay. But this is saying the expansion. This probably means I have to go. Oops. I need to go, unfortunately. All right. Well, enough for today.
All right.
We're so close. We almost have the last fundamental constant till we get to
ultra-radial space.
Ultra-radial space, but that's going to be somewhere else in the arithmetic hierarchy.
Right.
And we're going to be able to prove that we humans living in our universe can just never know anything about it.
Yeah, it'll be proof by construction of us trying to figure it out and failing.
Right. All right. Excellent.
Great. Okay.
Okay.
Well,
all right.
talk to you soon.
Right.
All right.
Okay.
Bye.
Bye.